Alright, should be making a video, response video to the PhysicistMichael guy who has made a energy video. Uh, Sorry, couldn't tell. It's sort of, I don't know how to describe it, right? I mean, it's a circular argument, so he uses his wrong ideas to defend his wrong ideas, and it's just circular. So he compares two formulations of how to detect something's energy, two mathematical approaches that both depend on the same fundamental error, time versus distance, and then says that's all I have to do. I mean, isn't that obvious? My broken equation gets exactly the same answer as my other broken equation, so what's the problem? And obviously, I'm arguing the problem is you don't have any evidence. So in 300, I point out that in 350 years, you've been claiming this, energy exists, this VV stuff, vis viva. I mean, I wonder if, I mean, that's kind of funny, right? Velocity, V, vis viva, which, means living force. Okay, so it doesn't sound very physicsy. This living force theory, okay, that is a complete kick in the nuts to Newton, Galileo, and Descartes, who all understood the universe and got right answers using momentum as the definition of energy. And a clearly different formulation, clearly hugely consequential. If you're going to say there is such a thing as conservation of momentum, there's no logical escape by your theory of destroying and creating energy with your theory. Every time you take the energy from a large object going slowly and put it in the small object going fast, like the gun and the bullet, for example, you not only violate Newton's third law, 2,000 joules on one side, 2 joules on the other side, you also create free energy. Because you basically say that if I do the two heavy things in the experiment with the explosion, I get 4 joules of energy from the fuel. And when I do it with the two light things, I get 4,000 joules of energy from the same fuel. I mean, these are real arguments, and he completely negated all of it, just didn't pay any attention to a single criticism, didn't pay any attention to what the argument is actually about, and says, there, I proved it with my bad math versus bad math. Sorry, but it's an insult, frankly. Okay, you don't want to take the argument seriously. I have asked multiple people, how much do I have to pay you to actually address the points I make? I will pay you to actually answer the question, does your kinetic energy work in space? That is, if I calculate a thrust, soda bottles versus dimes. I throw dimes out one side, with the same momentum I throw soda bottles out the other side. Does your kinetic energy, right, the dimes will have a lot more kinetic energy, does it turn a spaceship? Will you answer the simple question? I mean, can your science have credibility if for 350 years you say it takes 4 times the fuel to go twice as fast, and you don't have a single experiment demonstrating it? Not a single one. Physical experiment, not thought experiment. Anyway, just very disappointing. There's no way to, how do I interact in this world where it's just a waste of time trying to logically argue with people because they will pay no attention to the logical arguments. None. All right. So I say he does an experiment. It's when it's routine on the internet. This is the standard textbook babble, in my opinion. This is just their religion, okay? And they're telling us how the Holy Ghost works. And it's really uninteresting because it's not good physics. It's not good logic. They're misdescribing a simple thing, okay? They're looking at a photograph of a bear, and they're contriving a reason to call it Sasquatch. And that's all they're doing, because they're not even paying attention to something as obvious as 9.8 meters per second. Not per foot, per second. I mean, it's that bad, frankly, and you're just saying, what, is there a point? in interacting and attempting conversation. I mean, they won't address any of the arguments. All right, so I'll attempt to, well, here, I'll read his response, and it's just, I mean, frankly, it's just patronizing and mush. So he put it on the old video. Is this it? No, it's Huygens. Another, whatever. All right, so yes, this is all my polite requests, please, blah, blah, blah. He watched my response, and he, whatever, thinks he's got some sort of, and it seems to me, I think these can be simultaneously be satisfied. Let's see, one have and other, and also, well, here, I might as well just read it. Okay, I watched through the bulk of your response, and you seem to have a confusion between conservation of momentum and conservation of energy. No, the accusation is that Newton, Descartes, and Galileo all said energy is momentum. I believe energy is momentum. Okay, so it's not any issue of confusion. The confusion is, can you sustain your argument that you can conserve whatever momentum is and then pretend there's something called kinetic energy? All right. With kinetic, 1/2 mv, and also many other types of energy. So again, this whole idea that there's a type of energy. No, energy is just something with mass moving in the universe. That's energy. And you seem to think these can't simultaneously be satisfied. Yeah, that's right. They can't in a real experiment. Okay, this isn't the case, says you. Okay, for example, let's say, okay, I already countered that. Still, we're not going to go there again. All right, so just read his newest comment. I've put together a pair of videos testing some concepts with work energy conservation of energy that I'm hoping you'll find interesting. So it's exactly the same crap you can find anywhere on the internet. 100 videos probably, at least, well, thousands probably. It's the same rickety Scientific America type experiment, where they contrive a specific kind of experiment to try to illustrate what they're doing. It's like dropping round things into clay. Okay, it's a little specific experiment that if you look at it one way, their way, it'll give you the illusion, okay, that they're onto something. But if you analyze it rationally, like the rolling distance argument, if you analyze it fairly and realize certain things like, oh, it's only going half the speed after 3/4 the distance, that's not in the right place. If the friction was the same and the same energy was being absorbed, then it should be going half the speed, not at half the distance. All right, I go through multiple experiments. They're really not that many. It's all the same experiment over and over again, showing pretty much full details of the setup. Yeah, well, I don't know, whatever. Data acquisition analysis for experiment testing the work energy theorem. So he tests the work energy theorem against the work energy theorem. Okay, he doesn't test it against momentum. Conservation of energy involving kinetic energy, gravitational energy, and spring energy. And again, that's always the flaw, is all these experiments, they're generating the energy from gravity. Okay, so not a good idea. Anyway, if you want to know the energy in, you have to do the calculation. You have to figure out that gravity is about time. And if you think gravity is about distance, then you're going to get a wrong answer. So again, I made all these arguments in my previous video, the distance argument. I made the argument about how here's a gravitational body. I'm going to fly by the gravitational body. What's going to matter? How much distance I travel? The set amount of distance where the gravity is at all significant? What's going to matter? All that's going to matter is how fast I go by. If I go by really, really fast, I barely get any gravity on me. Okay, the gravity barely touches me. All right, I go really slow, the gravity beats the crap out of me. Come on. Can you counter that argument? That specific argument? Okay, anyway. Theorem, okay, elastic collisions, specific examples. Okay, the specific examples I give you with two masses launched off each other. So this is just the classic, put two carts together with a spring, break the spring. The twice as massive cart goes to half the speed. So I don't even know how that proves kinetic energy. I mean, obviously, because of the same mass, you can pretend the kinetic energy is conserved. But obviously, when the masses are different, the kinetic energy's number looks all funky. Professor Lewin admits it's all funky. He says you can, screw around with kinetic energy, but nature can't finagle momentum. All right, all the experiments support. It's just, is there any point? They'll just keep saying this and saying this when they don't have any experiments. And I could show, again, I mentioned the Mythbusters. There is a Mythbusters video where they do the car crashes, twice the velocity, only twice the crash. Not 4 times the crash. No evidence of 4 times anywhere. Jesus. To a fairly high degree of precision, the standard physics notions of energy. I'm sorry, they don't. And I guess they are notions of energy. They aren't really scientific theories of energy. Okay, I organized them as a standalone video rather than a response. That's right, so you didn't deal with anything I said. You just made a standard textbook babble video. I want them to be applicable to anyone. You want to brainwash little kids, okay, who stumbles upon them. But I did try to address what I understand to be some of your key issues with physics. So there wasn't a key issue anywhere in there. There wasn't one single one of my arguments addressed at all. So I'm just saying that's the fact. You can't find it. So go ahead. Somebody find a quote from the video that has something to do with making a comparison between momentum as a theory of energy and kinetic energy as a theory of energy. Show me one instance where he made that comparison. The first part will be available tomorrow morning. Okay, it's already up. Covering the work energy theorem, and the second part on Monday. The other parts I mentioned, which he's going to do the same thing. He's going to do his calculation and say, see, it's 2,000 joules, or it's 400 joules, or it's some number of joules. He won't in any way prove that it's that many watts. He won't light bulbs with it. He won't ever prove that the 5-ton train going 10 miles an hour has twice the energy of the 10-ton train going 5 miles an hour. He'll never show it. He'll never show it winning the tug of war. He won't show it lighting more light bulbs. It won't happen. Hope that bringing hard evidence from experiments. So this is not hard evidence. You didn't prove your joule number. You calculated it. I can calculate any number and say that's how many joules it has. I can say how many kumquats does it come to. Okay, I'll tell you how many kumquats it is. And I'll come up with 2 wacky theories that give me the same answer for how many kumquats it is. It doesn't matter. You didn't prove anything. You didn't show anything. We'll help you reconsider your positions. I'm trying to get you to reconsider yours. That is, go back, look at the history, recognize that there was no good arguments made in the history of the dispute between vis viva and momentum. They made no good arguments in defense of it. And they did a rickety little round things into clay experiment, and that fooled everybody. And that's it. That's all you have. Okay, on these well-established scientific principles. So again, well-established, like light is bent twice as much by gravity, and all you have is a crappy 1919 experiment done with a 2 o'clock eclipse, in the rain. And I'm supposed to be totally convinced. And I'm being rude and obnoxious to say, no, I'm not convinced. Gosh, it's just, all right. I mean, all I can say is, thank you again for the reply, but it's totally non-responsive. Yeah, I think that's what I said before, so maybe I'll just say that again. Thank you for the reply. I've made a response video providing counterexamples to your example. I think the subject is worth your time and consideration. I hope you will continue to participate in the discussion. Thanks again. Okay, so that's just based on when he would get around to making his video. But yeah, just totally unresponsive to any of the arguments made. All right, so I don't know if there's, I'll show the experiment, I guess, and then I could show him saying some crap, but I mean, none of the crap he said had anything to do with reality, so I don't know how much value there is in any of it. And of course, he doesn't have the experiment very... Alright, I'll just draw it. So,
let's see if there's a way that we can get a better handle on exactly how much friction is on this track and how much it would have affected our results.
Okay. So that is the key thing. Again, we're using friction, technically, okay, as a way of extracting the object's energy. So we're extracting energy from something by applying contact with it. And by the contact with it, you know, or pulling or pushing, you know, with a string or some kind of, you know, there's no pull, obviously. So we're just basically saying the more friction there is, the more energy I can extract from the object. And the less the friction, the less energy I can extract from the object. So that's the principle I'm arguing. Okay, if I have to say it that way, that somehow, I guess you disagree that that's how it works, but that, in my opinion, is exactly how it works. I probably need a little more than normal, so we'll go 125 is easy. Blah, blah, blah. All right, so, oh, you didn't see that anyway. All right, so we'll just get to drawing the experiment. So, I mean, this isn't much better than Brozo and Dispar. You know, it's the same idea that they have an experiment. They don't really theoretically pay any attention to what is actually going on. You know, that's the actual physical facts of the experiment. And they just jargon their way through it. So it's not very complicated. So you have a cart, a string, a pulley, and the string goes down, and you have a mass. That's it. Okay, not complicated. So cart on wheels, pulley, and mass. All right. And so what you're trying to ascertain is how much energy does it take to move the cart. And so we're using the idea of gravity is going to be the thing, okay, the energy source, okay, this mass falling this distance, okay, is going to create the energy source. Now, the simple argument I make, it's 9.8 meters per second. Seconds, not feet. Okay, so distance this falls. No. Time. I'm sorry. I mean, I don't know how to do this over. I mean, I've had to do it over and over again. This is what you're supposed to pay attention to. It's about how long you're being exposed to the gravity. So every second, every millisecond, every billionth of a second, gravity works on me. Now, because I'm stuck in friction, I mean very hard friction, very rigid friction, no falling friction with the earth, okay, all of the energy goes into the earth. So all of my energy that I absorbed from gravity, the sunlight hitting me, so to speak, it goes right into the earth. I don't get to keep any of it. Just a fact. And so that's what's happening when the mass is falling. So, I mean, let's say, okay, that it is true that all we're going to lose is 1% of the energy from the wheels and from the bearing. So the friction of this system is really low, very low friction. And so what's basically going to happen is there's a free fall speed for the weight, right? So if I dropped a weight from this distance, all right, and I let it free fall, okay, now you can't easily see that. Okay, I'll let it free fall. There'll be a certain amount of time it'll take to fall. So it'll be in the gravity a certain amount of time where it's collecting the energy and the ground, the friction, isn't taking any. Okay. And what's going to happen in this experiment is if I change, whatever weight I put on here, okay, because of this mechanism, it will not fall at the free fall rate because the weight of the car is now the friction. So I could put my fingers on the side of this weight and slow it down, right? Let it rub on my fingers, and I could slow it down, or I could tie this string to it. Okay, so the string is now the friction. So not the friction of the bearing, not the friction of the wheels, but the movement of the cart is now going to essentially represent how much drag I put on it falling. Now, as I put drag on it falling, the fact is it's now going to be in the gravity a longer amount of time. It's not just mg, it's mgt. Okay, the t is really important. So it's the amount of time it's in the gravity will be its total energy. So you could sort of understand the experiment as being any time, okay, longer than the free fall speed is time caused by the cart. So the cart's energy will be exactly the differential between the speed, the free fall speed, okay, and this speed. So the faster it falls, all right, and it will fall different speeds depending on the mass because the friction isn't going to increase, okay? This is the friction, okay, the friction. Okay, the friction is the movement of the cart. That's essentially the dragging force, the counter force, is having to push the cart. All right. So anything more than the regular amount of time it would take to free fall is the time in gravity that you have to account for. Because the total energy the object absorbed is the time it's in the gravity for the experiment. So if the experiment, if going from here to here takes 1 second, all right, and then I do the experiment with twice this mass and it takes 1/2 of a second, you can understand that's the falling time. And let's say the free fall time would have been 1/4 of a second. I mean, I guess I should have used the free fall time as 1 second, and then I could explain, But, I mean, the point is the gravity is constantly pushing on the object, and all you're saying is how much is some other force taking it away. Not some other force, but some other contact through this rope. Okay, how much of that speed is it taking away? And now it's in the gravity longer. So the smaller the mass I put on here, the slower, the longer it takes, because it's a small mass collecting a small amount of force, and it takes longer to move the car. And so it goes a slower velocity. And the heavier I make the mass, the closer I get to the free fall speed. Okay, now I'm going to go faster and faster and faster. And if I make the cart light enough, or the mass heavy enough, I can essentially be almost perfect to the free fall speed, because the friction will be so low. So obviously this is the whole subject. This is work. This is the reality. This is the energy of the system, is the force per second, how many seconds of this rate happened. All right. Now let's see, what else is there to say? We'll just go over his statistics, and I'll just point out how doesn't make any sense, and it doesn't matter because he's not making a comparison between momentum's answer, okay, which will work, okay, mv will give an answer, and it will be consistent. As I change things, it'll be just fine. mv isn't at all confused as long as you understand it's about the time and not the distance. So this is essentially exactly like the rolling ball example. All right, if you're not doing rigorous physics, and I'll say it that way, I don't know, there's no other way to say it. I mean, it's a pretty simple experiment, and you're just not giving it any fair analysis. And I give them, one I give twice the velocity to, and the twice as velocity one goes 4 times as far. I can account for that by just drawing a scale and just pointing out the faster I go across the scale, the less weight I'll register. Faster I go, less weight. Less friction, faster you're going. Just a fact. I'm losing less energy per foot here than I lost here. Okay? In here, this is 1/2 the speed here. Here, at this silly location. 1/2 the speed. See, this goes 1/4. It goes 1 unit of distance. So 1 velocity only gets me this. 2 velocity gets me 4 times. Same thing as going up in gravity, coming down in gravity. Galileo already declared that, and it didn't confuse him because it was 1, 3, 5, 7, blah blah blah, dot dot dot. He didn't go, oh, you square the velocity. That wasn't his conclusion. Newton wrote about it. Newton wasn't confused and said, gee, velocity must be squared because it travels more distance. Because I think he knew it's obviously about how long you're in the gravity. It's not about how far you're traveling. This travel distance this is not linear. This is not a fair extraction of the energy. You're extracting less energy per foot here. Less energy per foot. That's my accusation. Less energy per foot here than you did here. This is the same energy. This, when this gets all the way here, it has exactly the same velocity as this has starting. This energy is the same as this energy. This, same energy as this extracted from the object. That's the assertion, that's the fact I'm asking you to counter with some sort of reasonable argument. Is there any point? All right, so I'm just saying this is a classic experiment. He's got exactly the same equipment. It's a standard out-of-the-box experiment. Really doesn't have anything to do with anything meaningful. All right, let's start around 5. That's when he's doing talking about some elements of theory, but not much. All right, check the volumes. Oh, Jesus. It's just really... I can't pay them. I can't extort them. I can't humiliate them. I can't do anything to get them to argue the actual argument.
Potential energy do you have? There are other types of energies. We'll talk about those in other videos.
I'm saying obviously there's not other types of energy. Heat is energy. All you're saying is energy basically is there's scattered energy into tiny things, or energy like a school of fish. The energy is scattered. The fish are going in all kinds of directions, or the fish are in a school and they're going in one direction. That kind of argument. Laser beam versus a light bulb. You can focus energy and have it all going in one direction, or you can scatter energy and have it go in multiple directions, which means they'll counteract each other and not create anything you would call an effect you could see. It's still energy. It's just you can't see it anymore. I mean, if I make the spaceship go left and then immediately I make it go right, I won't see the difference. If it happens fast enough, I don't see it. I'm claiming that right now you actually are going into the ground. You actually do move into the ground. And then the ground pushes you back up. You can't see it because gravity's a speed of light force doing all this very fast and in very tiny amounts. And you can't see it. But the electrons and protons are doing it. Right now. You're doing a lot of moving.
But this idea leads us to the idea of conservation of energy, saying...
Okay, so again, this is something they all believed in. Descartes essentially was the first guy to really assert it strongly, that basically the universe is put in motion, and the motion is just moved around, and that's all there is in the universe. There isn't any mystery to it at all. It's just one hunk of motion. You just poke it somewhere. The poke just keeps ziggling through the thing, and it never stops because on the microscopic level, the tiny bits, there is no friction. Okay, there's no hidden little thing that takes the energy away. No, you have to move electrons, you have to move these things, they all have to conserve the energy, and it's forever. The energy never dies. It can just be trapped and stored, but it never dies.
The amount of energy, the amount of mechanical energy that I start with, plus any energy added by...
what's mechanical energy? So again, now we have a third term. So again, I'm sorry if you misunderstood my video. My video was making a comparison between kinetic energy, 1/2 mVv, against the simpler formula mv as a definition of energy. The correct formula, E equals mv, is my assertion. E does not equal 1/2 mVv.
Non-conservative forces, things other than gravitational forces, spring forces. There are other conservative forces, but say...
So all the energy has to be conserved in the universe is also my assertion, like Descartes, and I don't think they'll ever find any evidence where it doesn't happen except their theoretical subparticle bullshit. Okay, quarks can make energy and destroy energy. But outside of those little magical things, nothing makes energy and destroys energy.
Energy added to or removed from the system by me just pushing on it and doing work on the system just by pushing on it. Or forces like friction.
So that's a system. So he's saying I can change, I can add energy to a system that's storing energy. Like a pendulum, I can add energy because I can poke it when it's going in the right direction. If I poke it when it's going in the wrong direction, then I'm not subtracting energy technically, okay? I mean, it's not a fair way to say it. I'm opposing it, okay? But the opposition is real. There's real events. There's real force contacts, okay? And you have to actually put real force in to make it happen.
Air resistance. They can add or remove energy from the system. If I know how much energy I start with, and I know how much energy is being added or removed by these other forces, that will equal the total amount of energy that I'm left with at the end.
Okay, so this is where it's just nonsense, right? So this is where I do the gun in the gun example. So I put a gun inside of a gun. I use exactly the same charge as a regular bullet. I fire the charge. I get 4 joules of energy. 2 gun recoils is all I get. All right, I put 2 bullets in a straight tube. Same exact amount of TNT, and then fire it. I get 4,000 joules. So I'm just saying your theory doesn't make any sense at all. It's not conservational. It doesn't work. It mechanically fails to work with very simple examples. There isn't 1 minute the TNT didn't have 4 joules of energy stored in it, and the next minute it had 4,000 joules stored in it. That didn't happen. That's not real. Okay, momentum says everything's fine. 1,000 atoms going 1 mile an hour is exactly the same energy as 1 atom going 1,000 miles an hour. Momentum has no problem solving the paradox your theory creates.
It's our conservation of energy formula. And this allows us to study and do calculations for a lot of different kinds of systems in a pretty straightforward way.
All right, there's nothing straightforward about VV, okay? MVV. There's nothing straightforward about it. I mean, it looks obnoxious to reality. Why the hell is the V times the V? How do I square a velocity? Why would I square a velocity? It makes no sense at all. What the hell is that? That's not straightforward in any way at all.
Let me give you a quick example. Let's say I hold this object up.
So this is again how he describes what gravity is. Now I would change the example. So he holds it up. This I'll just say you drop it in a stream of water. Okay, what's going to happen to the object once you drop it in the water? Okay, the stream. And let's say the stream is pretty fast. Okay, we're not going to say the stream is just going very slowly, but whatever. There's a big, obviously with gravity going the speed of light, there's a huge difference. Okay, between you have a long way to go to catch up to go as fast as the stream is going. Obviously, if I drop something in a stream, it can be going the same speed as the stream pretty quickly. So that's where the analogy fails. But the analogy is that you're just putting it up. You're going to drop it. You're going to let it go in a stream. So my argument is yes, wherever I lift it to, I'm going to let it go, and there's a stream of energy. And the stream of energy is going to hit it with a pressure. And it's going to be a constant pressure because it has a certain size and it will capture a certain amount of pressure from the stream. So the stream will push it with a constant pressure, and it will, over a period of time, accelerate. That is, it'll start going faster and faster and faster because each push is permanent. it'll keep going in that direction as long as there's no counter force. And there's no counter force because obviously the stuff in front of it is going faster than it's going. So there's nothing coming from the opposite direction to counter its acquisition of velocity. So yes, she's going to let this go in a stream of gravity.
Okay. It's not moving yet. Sorry, need to make sure it's in the camera view.
Because it has 100% friction. So you've applied a 100% friction, therefore it can't move. If you apply 99 friction or 98% friction of the stopping pressure, then it will start to move. And it'll start to move very slowly, meaning it'll still be in the gravity a very long time, and most of the energy will still be absorbed by you holding it. And it won't be acquiring most of the gravitational energy, will still be going into the dampening source, your hand.
It's not moving yet, so it doesn't have any kinetic energy, but if I'm holding it higher up, it's going to have more gravitational energy.
Right. It's not going to have higher up doesn't mean more gravitational energy. It means longer in the stream. So all higher up means, the higher I go, it's still 9.8, okay, until you get, almost like a mile away. Anyway, so it's still the same gravity. Well, whatever. A few hundred feet. 100 feet. It's, only a tiny difference, okay. 9.8 is on the surface, and blah, 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 blah. And you go a little tiny bit higher, it's 9.8 points, whatever, 9.81111, and then it's 9.82222. And 3333, that kind of thing. But it's such a small difference, it doesn't make a difference for any of these kind of heights. So the point is what is he doing? He's just saying this is how long I'm going to let it sit free fall, free push in the stream. That's all this is. This is the distance the stream is allowed to work on it without me taking away the energy, without me applying a counter frictional drag force. Clearly.
If I let this object go, it falls downwards, and as it's falling, it's going to a lower position, so it's...
So, again, he keeps talking about its position in space when all that's going to matter is the time it takes it to acquire a velocity. The faster it goes, the less energy it can collect in a portion of distance, because the gravity is 9.8 meters per second. Not per position, not per foot, not per inch, not per centimeter, not per micrometer, not per nanometer. No, it's per second. It's per a unit of time. How long did you let it fall freely in the stream? How long did you allow it to collect all of the energy without you taking any away through friction or drag? And that's all that's going to matter. The time will tell you the right answer. It'll tell you how much energy it collected. Jesus.
Losing gravitational energy. But that energy isn't being eliminated from the universe. That energy, as the object falls...
Obviously, it's not being eliminated from the universe, but the fact is the impact weight, will not be, again, position relevant, 4 times the distance will not mean 4 times the weight. It'll only mean twice the weight, and it'll only mean twice the velocity, and only be twice the time. So again, all those 2's, and you're telling me the right answer is 4.
That energy is being converted from gravitational potential energy.
So there's no conversion of energy, there's theft of energy. You're stealing the gravity, The energy of the stream is diminished when you drop something in it. You're stealing the energy from the stream to give your mass motion. Your mass has now collected the energy the stream had. The stream now goes a little tiny bit slower. You could understand if I drop a big enough mass into the stream is going to go much, much slower because I dropped a big giant mass that it has to push and it has to use its energy to push it.
To kinetic energy, the energy of motion. And again...
All right, so all energy is motion. That's all there is in the universe that's energy. Something's moving, a something. And I would argue a something has to have substance. So it has to have something called a mass. So if it's a something, it has to have mass, and it's moving, and therefore it has mv, and that's all that matters. There's nothing else in the universe. That's my contention. That's my counter argument to your theory, and I will argue there's not a single experiment on the face of the earth that demonstrates that theory to be incorrect. It works in space, it works on the ground, it works everywhere. As long as you understand that gravity is a time-dependent force, no problems at all.
According to this claim, we should have a balance for the total amount of energy that system has during that entire motion. These are
right, and there won't be a balance because you're going to say it's 4 times the distance, therefore it should be 4 times the energy, and yet it'll only land with twice the pressure. It'll only land applying twice the pressure, twice the weight.
Some of the things that we're going to be testing out. So let's have a brief look at some of the tools that we're going to be using.
Standard crap. Again, it's just this, these are standard, they just keep doing the same thing. They just keep dropping the round balls into the clay, and there's nobody apparently smart enough to understand what actually is happening in the experiment, that it's a time-dependent experiment, that all you're doing is changing the amount of time the mass is in the gravity. The longer it's in the gravity, the more energy it's going to collect, but it's completely dependent on the size of the collector. So if I make the mass lighter, it'll be longer in the gravity, but it's a smaller mass, so it's not going to collect. It's going to collect, let's say it's half, it's going to collect half the energy. So it'll end up being the same energy being actually taken in by the cart. If I make it a half mass and a half cart, I'm going to have the same circumstance.
On this track, I have a relatively low friction track here, where you've got a cart that can move on that track. I've got a
So this is really uninteresting, and it's in a kind of like, again, hundreds of videos. Standard classroom propaganda is what I'd call it.
Motion sensor set up at one end that will send out sound pulses, which reflect off the cart, go back, and you can measure where the cart is based on its position. So if I start my...
Right, so instead of... You could also calculate its velocity using the same sensor, and he doesn't do that. So nowhere in this experiment does he talk about velocity. So he just punches it into the computer. Somehow the computer's calculating the velocity, but we don't get to see any of that. And he's just obsessed with position. How far did it travel? And that's all.
Sensor. If I move closer to the sensor, that position goes down. If I move further away from the sensor, well, that position goes back up. So this can track my motion, the motion of this cart, and we're going to need that in order to calculate, well, what is the kinetic energy? We need to know how it's moving to get that kinetic energy. I also have a force sensor attached to this cart. So there's a little hook on the end here, and if I pull on that hook, you'll notice that the force value is changing. So
it's just weight, all right? So that's just the weight part. So he's going to be applying a constant weight to the cart, all right? So you're basically, all the string and the pulley are going to do is convert it into a constant force. And what won't be constant is the velocity of the cart or the speed with which the mass drops. Those aren't constant, and he's pretending they are.
Let's say I were to attach a string to this hook. If I start pulling just a little bit on that string, we only get a small amount of force. If I start pulling harder, then in this part right here is where we're measuring our force. If I start pulling harder, I'm going to measure a larger force. And
so that's just the weight. You can't change the weight of the dropping object. So no matter what speed it's going, it still weighs the same amount. Okay? So, but the fact is that it's going to go through gravity at different speeds. And so there's going to be a unit of time, is the unit for which you're going to collect the force, is over time. You're not going to collect it over distance. It's not the right way to say it exactly, but, well, it's close enough.
This force sensor is going to be involved when we're trying to calculate things like how much work was done by a particular...
All right, so again, this word work doesn't mean anything. Work is just the part of a matter in motion that we call useful, and then we'll say that's work. But for all reasonable argumentation, work is a redundancy. It's a synonym. It's superfluous. Work is energy. It's just one part of the system's energy. So if I make a laser beam, there's a certain amount of work that you'll see in the beam. Some of the work you'll see in a bunch of heat and other things that I'm generating to create the laser beam. So some of the work will go places that I won't consider work, but it's real. Just like holding this pen up, I am in fact doing work on it. It's a fact I'm doing work. It would be ludicrous to say if I'm holding 100 pounds in my hand, I'm not doing any work. But their theory actually says that, because they're just talking about the useful part. They're not talking about the useless part.
Their force. So we're going to be doing a couple of experiments, and let's look at the first setup that we're going to have for...
Yeah, it's really this... well, I guess there's... Yeah, he does a second spring experiment, but again, that one again, I can just say, well, why don't you do the comparison to momentum and the answers momentum gets? Because those answers are going to be just as good.
One of our experiments.
See, none of these experiments involve the conversion of the energy from a large mass to a small mass, or a small mass to a large mass. So without those conversions, you can make up any numbers you want. The real test is testing it with different masses.
So in the first of these experiments, what we're going to try to test out is this work kinetic energy theorem, where the net work is equal to the change in kinetic energy of the object. So
who says... So right there, it's almost crazy. He's going to multiply the distance it travels times the kinetic energy and say that's somehow a useful comparison. So again, this is just multiplying a cause times its own effect. What would be the point of ever doing that? Why would I multiply a cause times its own, the effect it caused? It can never be useful. That's like putting the ingredients in the cake after I baked it. So I baked the cake and then I put the flour in.
Our claim is that the net work is equal to the change in kinetic energy. Again, this is what we are going to...
Whatever. I mean, it's just all he's really saying is that the drag placed on the weight that is collecting the energy. So the weight's the source of the energy, the falling of the weight. All right, and the fact is that all of the drag, the friction that'll stop that weight from falling at its free fall speed, will entirely be generated by what energy it takes to move the cart. So the motion in the cart will equal, okay, the difference in the amount of energy you collected. But the thing he's not going to pay any attention to at all is how long it takes it to fall, which is how much energy it collected. It collected energy based on how long it's exposed to the force per second, 9.8 meters per second. The units of force are coming in units of time. And obviously, the heavier the cart you push, the slower the weight falls, because it has to collect more energy to move the bigger cart. And it has to take time to collect more energy.
To test. And the way that we're going to calculate this net work is by looking at the area under this force.
So I could do this as just arguing this is essentially creating a ramp. So this is like Newton's ramp. And all you're really saying is I'm going to create drag, okay, and the drag is going to absorb all of any extra energy caused by more time. So the same proportionality will exist. The drag will consume all of the energy, all right, that the extra time it takes for the object to hit the ground. So I'm just increasing the free fall time and taking all of that extra energy by that increased time, that extra gravitational energy, and I'm heating the ramp with it.
Versus position graph. So let's write this as area under force versus position.
So let's just say area under is just another way of saying I'm going to multiply the things times each other. So he's going to multiply the number of joules of kinetic energy times the position. Now, why would that work?
And the change in kinetic energy is just going to be our final kinetic energy minus our initial kinetic energy. So how are we?
So, right, so we have 0 because we're starting with nothing. So, yes, so no problem with that. But obviously I could just do initial momentum and final momentum. Not complicated. MV is the only part that really matters here.
Actually going to test this? Well, the setup that I have is a half Atwood machine where we have this low friction track.
Right, so this is exactly the same video done by hundreds of other physicists for decades. Totally yeah, it's not a response to somebody who's already seen it and argued against it. So I guess I could say. But this is just round things into clay again. Just repeat the 1700 experiment until you fool everyone.
And I should probably draw this one. So we're going to have this low friction track. I've got a pulley at the end of this track. And we've got our cart. And attached to this cart, attached to the force sensor on this cart, I'm going to run a string over that pulley, and I'm going to attach some hanging masses at the end.
Right, and the hanging masses will go right through the string, the weight, right into the cart's force sensor. So all you're doing is using the cart as drag. The cart is now a friction source stopping the weight from free falling. So the weight can't free fall because you're applying a frictional drag connected to this string.
So we're going to have a string going over this pulley and have this hanging mass at the end. So that's going to be our hanging mass. What we're going to try to do is the motion sensor.
So he says mg here. It's not mg. It's mgt. But whatever.
Which again is right at this end of the track. The motion sensor is going to track the motion of the cart so we can calculate what is the kinetic energy of the cart at different points along the track. We're going to be monitoring how that kinetic energy is changing. And then our force sensor is going to be able to measure.
All right, so, this part I don't understand just because his numbers don't come out the way they should. Like when it's twice the velocity, he's not getting 4 times the kinetic energy, and that's their actual theory. So again, you'll see here that he's doing this calculation of the velocity without us seeing it. So we don't get to see that part. We don't get to see what the velocity of the cart is. It's not on any of these charts. So something pretty fundamental isn't available.
What is the force of tension in that string? And as that force is applied along that displacement, we're going to be able to calculate how much.
Yeah, sorry about that. Well, you can see it's a very small image, so you're not really missing anything. My drawing was pretty complete, so, you haven't missed anything.
Much work was done. We were going to try a few different hanging masses. The hanging masses are just so we can try this with a bunch of different forces and see if this work kinetic energy theorem holds up under a variety of circumstances.
So he's going to double the amount of weight, in my opinion, doubling the velocity, and he'll only get twice as much kinetic energy, which doesn't make any sense because by their theory, twice the velocity should be 4 times the kinetic energy. But again, you'll see he's just writing numbers down here and saying it's 250 joules. He's not measuring how many watts are in the system. He's not doing anything to collect that energy to say this is how much energy it is because I collected it in some real way. I made something happen with the fuel to measure how much energy the fuel had. He's not going to show us any of that. He's just going to throw a number on the table and say this is what I calculate the answer to be, and see my answer agrees with my answer. And I'm just saying the two theories are both broken.
So
it's force times time, not distance. So the top chart has force times distance. The bottom chart has energy times distance. None of them are time related.
Adjust my camera back so hopefully we can see the end of the track. A couple of things that we do need to make sure of. We need to make sure everything is properly calibrated at the beginning of the experiment. So these force sensors, I'm using vernier equipment for all of this. Force sensors in general, these types of force sensors, they do tend to drift a little bit over time, so I am going to have to make sure that when there's no force attached, I'm zeroing this force sensor. I also want to make sure that as close as possible, this track is level. I've tried to level it out ahead of time, so if I give this a little push in either direction, it shouldn't have too much of a difference between that. It's a very low friction track. It's not a zero friction track, but we'll see if that affects our data in a little bit.
So that was the one thing that was valuable, is he did the experiment a few times, got numbers, and he basically went into the point about you can basically figure out how much of this is waste energy, that is, it didn't go into the cart. And, it's a small percentage that the little pulley is using and the wheels on the cart is consuming. A small percentage of the energy is lost to actual friction. Now, my argument is from the weight's perspective, actual friction, that is, energy being lost to heat, is no different than the drag friction created by having to push the mass, the cart. So from the string's perspective, the two frictions look exactly the same. The string can't tell the difference between the friction lost to heat and the friction lost to the motion of the mass.
We're also going to need to get the computer to calculate some very specific things. So first, we said that we're going to be looking at the area under a force versus position graph, so I need this to be a force versus position graph. We also need to get the computer to calculate what is...
I don't know why they say versus. It's multiplied, so they're just saying a force times position. Force times. Well, I don't know why. Why would I multiply the force times the position when I know the force is 9.8 meters per second? Duh.
Is the kinetic energy of the cart. So we have to tell the computer how to calculate that. So this might be a little bit small to read. I was trying to get it to zoom in, but doesn't seem to be working. Let's call this kinetic energy. Call it KE. It's in units of joules. And we have to tell the computer how we're going to calculate this value. Well, our...
you can, I guess I could try to blow something up, but it's probably not worth it.
Kinetic energy formula is 1/2, so 0.5, times the mass of the object, times we need to tell the computer to use the velocity data, and we want that to be squared. So in here we have 1/2 m times velocity squared. We also need to tell the computer, well, what is the mass of this cart?
So we don't have any chart. There won't be any chart that's going to show us the velocity of the cart as a number. Okay, all we're going to see is a position of the cart. So totally useless. The whole thing will be contrived, okay, out of where in this 3.6 meters. So the whole thing travels 0.6 meters. So his scales, if you actually look at them, it starts with 0.2 instead of 0. So when it says 8, there aren't really 8 units of distance. There's only 0.6 of a meter. So there's only 6 units of distance. So, it's all kind of sloppy in the sense that you put zeros at the beginning. You don't put a 0.2 and then go 0.4 and then 0.6 and 0.8. No, you go start with 0, then you go 0.2, 0.4, 0.6. But anyway.
Does not know that ahead of time. So I've got a scale over here. And let's take that scale, move over here if I have just enough room to do this, put that on our scale, and if I can get the cord out of the way, that looks like 896.7 grams. 896.7 grams. So let's put that into here. So 0.8967 kilograms. And now we've told the computer how to calculate the kinetic energy of this object. So we're going to have a kinetic energy versus position graph. Just doing
so again, it's kinetic energy times position. So somehow the kinetic energy is what's causing the effect of its position. Frankly, its position isn't creating the kinetic energy. It's not the other way around. But at any rate, these two things cannot possibly be mixed as ingredients to make a cake. Okay, there's no point in multiplying the kinetic energy times anything, frankly. The kinetic energy is the work done by the entire system, all by itself. That's all you need to know. So we already answered the question by getting the kinetic energy. Now, the question is, how did it measure the velocity? Because it has to be doing the time thing to get that right. And we don't, he has time as a category, but we don't get to see any of that.
Little bit of housekeeping, making sure those graphs are linked together, so those axes are fixed. We are not going to need that much distance on here. Okay.
So I'll try to, I really can't see it. So he says it has velocity here in meters per second. He has the arc, which isn't going to be relevant, and then the KE.
The specifics of the experiment are, I'm going to attach a string to...
The arc would only, I guess, be relevant if he tilted the track to create more drag or less drag.
This. It's going to be connected to that hanging mass, and we're going to be able to measure how my force changes with position and get that area, and look at how our kinetic energy is changing.
So these are 2 times distance equations. So he's using 2 equations where he compares times distance to another equation that's times distance, and no equation that's times time, which the force is acquired in units of time.
And ideally, if this claim is true, these should match each other.
So garbage equals garbage, frankly. Garbage formula equals garbage formula. And they match, therefore the garbage must be correct because I have a bad formula and it matches the answer of the other bad formula. Therefore, we have solid proven physics. So the whole accusation I'm making is your formula is garbage. 1/2 mv squared is not real. It's a fable. It's nonsense. It never, ever, ever, ever gets the right answer. Just like the Young analysis of the double slit never resolves a double slit. It never gives you the positions of the fringes in a double slit pattern because the Young analysis never creates a double slit pattern.
Let's start with just a 50-gram hanging mass. Again, the hanging mass value itself doesn't really matter. We're just using it to generate different forces, which we are going to measure with that force sensor. So let's hook that on the end of the pulley.
So, I mean, you can really understand, right? There's string is going to be applying pressure to the cart. It's the same amount of pressure. It's a constant pressure. That's what the force detector is detecting. And what are you going to say is, well, how long did you apply the force, right? If I apply the force for a millisecond, I know I'm not going to put much energy into the cart. I apply the force for a full second, yeah, it's a lot more. If I apply the force twice as long, it's going to be twice as much. Just as Newton said, twice the force equals twice the velocity. You want something to move twice as fast. Those are his exact words. You want something to move twice as fast? Apply twice the force. You want to move 3 times the speed? Apply 3 times the force. So again, they are arguing that Newton didn't have right answers and that Newton didn't know what physics is. That's their overt statement. We've chosen living force physics, okay, not Newtonian physics. And they won't account for that's what their choice they have made. That's what they're investing in. And it's just plainly wrong. The argument was lost 350 years ago. And again, it was resurrected like Scientology or something. A cult member resurrected it.
Just a little bit so you can see the pulley at the end. This string is going over the end of the pulley. We're going to try to get as large of a range of data as possible. Let me take the mass off just for a second to make sure my force sensor is zeroed. We can do a little bit better than that. So I'm going to re-zero that force sensor. And I think we're ready to take some data, so make sure everything's set.
So, I mean, compared to the other videos on the internet, frankly, this is pretty crappy. It's a tiny little inset of the actual experiment, just a bunch of this paperwork here saying the same shit forever. And, so I'd argue, this isn't a great step forward in physics propaganda.
Set up for this. Good to go, and here we go. Okay, so let's scale both of these graphs. All right. So we've got how our kinetic energy is changing with position, and simultaneously we have how much force is applied. And since we're generating this just by having that hanging mass on the string, that force is going to be constant. So
all right, so he fixes these charts to look the same, so the resolution changes. So you have to pay attention to the numbers. The numbers are telling you. So the force will double when he doubles the weight. So the force is 0.5. It'll go to 1. I mean 1. So the force will, in fact, double as he doubles the weight. Here you can't really see. This has kinetic energy over here. So this isn't the velocity here. All right, so he could have measured just the velocity and put that on this chart. All right, and then we would see the Galilean truth. We would see that it's going half the speed after traveling 1/4 of the distance. Okay, so we'd see that the half the speed isn't in the middle where it's supposed to be. Okay, it's way at one, it's skewed to one end, indicating that the force was collected in units of time, indicating that in the first unit of time, the same amount of force was collected that it was collected in the third unit, because it is a time-dependent force. It's a constant pressure per unit of time, not per unit of distance. Because you have a velocity. You're going through that time quickly. I mean, you're through that distance quicker. You obviously collect less force because you're in the force less time. I don't know how this can't... I mean, what about this is hard to understand?
let's pick a range of data. We can pick really any range of data that we want for this. And for the force graph, we want to look at what is the area underneath that graph.
All right, so these are essentially two different equations, okay? Multiplying the force times the distance, and then he measures kinetic energy times distance. And those are the two formulas. I don't know why we would even do this second one. It doesn't even make any sense, so frankly. But they're both wrong-headed in the sense that the distance, obviously, as you're going faster and faster, the amount of force you're collecting is going to be smaller and smaller per unit of distance. Just like in gravity, the faster you fly through the gravity, the less gravity you're collecting per foot, per a unit of distance, because it's 9.8 units of energy per second. Not per foot. Per second. Not per foot.
So in this case, the net work, the area under that graph, let's call this trial 1. So this is trial 1. The area under that graph was 0.271 newtons times meters, which is the same as a joule. If we can scroll down just a little bit so you can see that in a little bit clearer.
So he's also demonstrated quite clearly that newtons can be directly converted into joules, and joules can be directly converted into watts. So he's basically saying there's an amount of wattage. All these units, again, are in units of time, by the way. You measure a watt by measuring an amount of time it takes for a certain amount of electricity to pass.
And now we also need, over the same interval, we need to look at the same interval, or as close as we can get to the same interval. We need what is the change in kinetic energy for that particular interval. So let me highlight, again, as close as we can to the same range of data. And we can calculate what is the change in that kinetic energy. So that's our delta y. So it looks like we got 0.247.
So I'm just going to point out that these numbers won't match. So when he has twice the mass, he's not going to have 4 times the joules. I mean, twice the velocity. So when he does that with twice the mass, acquires twice the velocity in the cart, he's not going to have twice as many joules, which somewhere something went wrong, because your theory is it should be 4 times as many joules.
This one is 0.247 joules. And again, if the claim was true, we would expect these to be a match. Now you're probably noticing it's not quite a match. The area under our force versus position graph was a little bit larger than our change in kinetic energy. Let's see how far off we were. Let's take the difference between those. So 0.271 minus 0.247. I got 0.024. So let's add a column over here saying the difference. So
that's the waste to actual friction. All right. So that difference, this 0.027 or whatever he said is, that's the actual friction losses. So small percentage of the total energy put into the cart was lost to heating the wheels, let's just say.
Is 0.024 joules. We might note that these are relatively similar to each other, but there is a little bit of a difference. If I have the 0.271 going to 0.247, it looks like we lost, I'll probably put in post, I'll put in a little like actual calculation for this, but it seems like it's around maybe 8% off. We lost about 8% of that energy. It's a pretty good match, but let's see.
Didn't he just put it up 8% to 0.24 isn't 8%, but whatever. Whatever. Yeah. Yeah. Oh, well, anyway, moving on.
If we can try this for a few more cases and see if we can get any better data. Another thing that's going to be helpful to note is that this range that we were looking at was around 0.6 meters. So if I move down in there, yeah, that range that we were looking at was around 0.6 meters.
Right, so let's understand, it looks like 0.8, okay? This says 0.8 in the actual thing, so it's deceptive because he's starting at 0.2. So, yeah.
We might be using that a little bit later. So let's reset, and I'm going to add another 50 grams to this, so we're going to be generating more force, and see what we get for this changing.
So he's basically should just say, look, it's twice the weight. Okay, what's the expectation? Twice the weight, it should be twice the force, right? But the catch is, these aren't falling at the same rate. These won't be in the gravity the same amount of time. So he's applying twice the weight, which should be twice the force. But the fact is, it's not going to be twice the force because the weight, okay, I mean, it's going to be negated by the fact that the weight now will fall faster. So it'll be in the gravity less time.
Kinetic energy. So again, I'm going to make sure that my force sensor is still hopefully zeroed. Sorry, there's a lot of windows on here.
So the force will be twice, but it'll only be for a much shorter duration in time. So the time will be cut in half. So again, he's going by the distance. He's not going by the time. So if he went by time, he's going to get twice the force with a heavier weight. But this is where the square should be. If he did the time chart, this is where the chart ends. So this line will go twice as high for the new experiment. The point is that if he charts it by time, how long does it take the weight to hit the ground, right? How many units of gravity could it collect? Did it have time to collect? It's units of gravity per time, a unit of energy per a unit of time. Then he's going to get the same area.
Looks pretty close to zero. So let's attach this, get our hanging mass. So again, now we've got 100 grams attached to this instead of the 50 grams. But again, that's just to generate a different force. So let's rerun this. Here we go. Okay, so we're going to have to rescale these graphs. And right. I think we can kind of just use this.
Okay, so before it was 0.5, now it's 1.0 almost. Okay, so we doubled the amount of force. That is, doubled the weight being applied to the cart. But as you can see, the cart went much faster, which means the weight fell much faster through the distance. So the weight was only in the gravity, falling, free falling, much less time. Because you're putting drag on it, there is no constant velocity. Okay, as you change the drag, you change the velocity. So he changed the mass, which is going to change the drag, which is going to change the amount of time it's in the gravity. The heavier mass doesn't need as long in the gravity to collect the same energy as the lighter mass. The lighter mass needed more time to collect the energy to move the cart. The heavier mass doesn't need the same amount of time.
Same ranges. We didn't change the range from last time. This one seems to be going a little short. I'm just going to reset these anyways. Let's redo these ones. Try to get approximately the same range for both of them. We've got the area under that graph. And we've got our change in kinetic energy. Let's look at change in kinetic energy. Okay, so in this one, trial 2.
All right, so let's understand it's twice the distance in the same distance in twice the time, essentially. Again, he's using the already calculated kinetic energy, so it's not like he's using velocity. This is not a chart of velocity.
The area under our force versus position graph was 0.504 joules. Our change in kinetic energy was 0.485 joules.
All right, so this is the part that doesn't make much sense, right? I would argue it's going twice as fast. As a fact, the velocity is now doubled because you put twice the mass on. Twice the mass only needs half the time to collect the same energy. But the fact is it's giving away the energy twice as fast. So I have to calculate that in. But regardless, shouldn't twice the velocity be 4 times the joules? So I can't be sure it's going twice the velocity with twice the mass. I have to think about that. It's in the gravity half as long if it's twice the velocity, and it's twice the pressure for half as long. So that wouldn't be, that would obviously be the same amount of energy in the cart. And obviously the cart has doubled its energy because it's going much faster. But regardless, I just thought it was curious that their prediction should be that there's more. If it's going twice as fast, clearly the 485 number isn't twice as the joule, so that seems broken.
Again, they're close, but they are a little bit off from each other. Let's calculate the difference. So 0.504 minus 0.48.
So what would have been very useful, these time numbers don't tell you anything. 230, 227, 228, 223. I can't glean much from those numbers. So let's see if the other chart I can read them. So we're at 0.2 in terms of time, 220, let's say, 225. I don't know why, I don't know, is that the average? The average isn't, well, I don't know if the average speed would help. Well, let's just see if the other number is 1/2 of that. Let's see, how far back do you have to go? No, it doesn't appear. It appears to be the same numbers, 228, 243. So the time numbers aren't telling us. See, it says position here now instead of time. So, now velocity is in here. So yeah, so velocity, so he's changed the order of these numbers for whatever reason. So now the velocity number is 120, 113, 103. Okay, so let's go with the idea that, yeah, one number is 110, the other number is 220. So we've doubled the speed. So we doubled the speed, and yet he's calculated the kinetic energy to only be twice as much. It's supposed to be 4 times as much, right? I mean, that's their theory, so I'm just saying. Something seems wrong there, right? All right, where was I, unfortunately? Okay, there's the number, so we'll just say what was there.
We've got to rescale both of these.
So this is the third try, I guess. Yeah, so it doesn't get to...
And again, I want to make sure that we're still getting the exact same...
So I don't know what really... Something went a little bit haywire here. He's got a little jitter at the front, and he's obviously... So maybe the hand release wasn't too good, because he never really acquired 1.5 the force. So he added another 50 grams, which should have increased it another 0.5. And it's clearly didn't make it for some reason. But because he's doing exactly the same, these two equations are measuring the same thing, so they're going to come out consistent because they're measuring the same thing, which is the wrong thing to measure.
Matching terms for both of them. So let's do that. Get the area under there. And try to get the same range. Just trying to highlight the exact same range. There we go. Going to get the same range for our kinetic energy data. Okay, so we got 0.743 for trial.
All right, this is a little funny because this line is crooked for whatever reason, so his selection apparently doesn't select in squares, which is kind of weird. So I don't know how exactly you're getting the right answer if you're not having the actual square. It's not a real square, so, but whatever.
3. So 0.743 joules. And our change in kinetic energy was 0.722 joules. Okay.
So again, it's, the number is just another unit of joules higher. So it's not doing the 4, 9, 25 thing.
Again,
it's not appearing to be velocity times velocity. There's no velocity squared indication here. So I should see if I can see the time number. So let's see, position velocity. So now it's 1.2. That's way off. So I don't know what the 1 is. He has one here, 312, 316. So I guess that's the final velocity is 360. The velocities change. This velocity number changes the whole time, so it's really hard to tell whether. And he hasn't selected the final velocity. He selected short of that. So it says 290. So again, that's 290 would be correct because obviously it is less force. I mean, it's not as much force as it should be. It should be 1.5 force, and he's short of force, right? Yeah, this is force. So it's short. And so the velocity is indicating that shortness. It's only 300, so it's a little bit short of what it should be, which is 340. The momentum would say. Okay, so that makes sense now. So I these numbers you have to take them with a grain of salt because frankly these force numbers don't match these numbers at all. I mean, clearly it was less force. It should be less joules. It should be off 247 times 3. All right, so 4 times is 12. Yeah, so it's pretty close to 3 times. It shouldn't be because obviously the force was way short of the full unit of extra force. It's short of the 1.5. 0.5 for the first experiment, 0.1 for the second experiment, 1.5 for the third experiment. That's how it should be. And that's his numbers are indicating, his joules numbers are saying that, but his force numbers aren't saying that. So again, there's lots to find fault with this experiment, frankly. Lots of dubious stuff.
A little bit off from each other, but there's always going to be some measurement error in any experiment that you ever do. So we have to be able to evaluate, is this error explainable by our experimental setup, or is it a sign that our claim is actually false? But let's do this difference again, 0.743 minus 0.722. I got 0.021.
All right, so again, he's comparing to these two equations, which I'm both arguing are dependent on distance being linear. That is the same amount of force over the same amount of distance. Clearly, it's not the same amount of force over the same amount of distance. It's the same amount of force over the same amount of time.
And this would only be, I'm guessing, around 3%. 3% of the original energy. So they match, again, within about 3%. That seems to be a pretty good match. But let's go a step further and see if we can find any patterns in the errors of this experiment. Okay. Because you might notice that in all of these cases, the area under the force position diagram, the work done by that tension force as the cart is dragged along the track, is a little bit larger than the change in kinetic energy that we had. Let's see if we can maybe come up with a reason why. I mentioned that this track is a low friction track, but it's not a zero friction track.
All right, so I'll just point out again that all you're really saying is that all of the friction goes through this wire. The string is the friction against the mass moving. So all of the time, okay, that it takes for it to go, that takes longer than its free fall speed. So anything more than its free fall speed is energy being put into the cart and the friction. And the point here is that the friction is a small percentage, 1, 2, 3% of the total energy that went in the string. So the string energy, say, was 200. The amount of energy that got to the cart is only 198, whatever you want to say. So yes, a little percentage went to heating the wheels. But again, it's just about the mass is only collecting gravitational energy while it's falling. As soon as you have it hit the ground, obviously it can't collect any more gravity because it's all going into the ground. So the string only collects while the mass is falling, and it's the amount of time it's falling is the amount of force it can apply. It's force, okay, times time.
There is going to be a little bit of friction. So on top of this, we should also say there's going to be a little bit of a force of friction acting against the motion of the cart. And that little bit of friction going in one...
So again, the friction isn't acting against. The friction is just you losing your money. So if the energy was money, friction is just a thief that pulls the money out of your pockets. You're giving the money to the friction. So it's the energy being lost to friction. It is not a counter force. You don't need something to make you poor. When you give your money away, you are made poor by giving it away. There's no force making you poor.
Direction, so that as the cart moves down the track, the force of friction is going in the opposite direction. So the work done by friction should be negative. Because
there's no work being done by friction, okay? So there's just the energy that is dragging on the weight. And you're just saying what portion of the energy is being absorbed by the wheels and the pulley and what portion is going into moving the cart. And clearly, yes, a small percentage goes into real losses to heat. Real friction, okay? The moving of the cart is now a form, as I said. He called it dragging, okay? It's dragging the cart. The cart is drag. It's a form of friction, but, it's not a classical form. It's not heat loss. We are actually creating visible work, okay, in the sense that we can see the object moving. But its movement has to be taken from the movement of the mass falling in the gravity. Obviously, it isn't moving at its free fall speed because we're taking the energy to move the cart.
The direction that it's moving in and the direction of that force of friction, those are opposite each other. So the force of friction should be doing a small amount of negative work. That would have the effect of decreasing.
Obviously, losing your money is negative to your checking account balance kind of thing. So yes, you wrote a check, your balance goes down. It's not negative energy in any way. You gave something you had away. You don't have it anymore.
This net work by a small amount. And you'll notice that these three trials, the difference between the work done and the change in kinetic energy, we always had a little bit more work, and it was by almost exactly the same amount every time. The presence of a small amount of friction in this track, which there definitely is, the presence of a small amount of friction would take some of that energy away from the system, which will not end up as kinetic energy. So that friction would decrease these values by a small, similar amount. It's the same cart, it's the same surface for the work done.
Right, and we're basically saying the work done is only twice the work. So twice the speed, twice the work.
We picked a range of data that was pretty much the same for each of the trials, so the distance that the cart traveled. This seems to match very, very well if we say there's also a little bit of friction doing a small amount of negative work on this system. Let's see if there's a way that we can get a better handle on exactly how much friction is on this track and how much it would have affected our results. So what I'm going to do is just push the cart down the track.
So I'm just saying this is sort of uninteresting. It's already well established. It's a tiny bit of friction, blah, blah, blah. The numbers sort of indicated. It's sort of, everybody can sort of intuitively understand it's kind of low friction. It's a small amount of energy that we're losing. The pushing energy is a lot more than the amount of energy we're losing. But instead, he decides to just go into what I would consider completely unnecessary detail, but whatever.
Measure using the motion sensor what is the acceleration of the cart. And from Newton's second law, we can say the net force is equal to the mass times the acceleration. And if friction's the only thing acting on it...
Right, it's the mass times the velocity, actually, but whatever, the change in your velocity. So it's just mass, it's just the change in your momentum. The force equals the change, the net force equals the net change in your momentum. That's what Newton said. So, again, it's this, I have to say, I think people are really horribly unfair to Newton's physics, because he didn't say what they say he said. What he said was twice the velocity, twice the force, not 4 times the force.
From the acceleration and the force, from the acceleration and the mass, we can get the force, and if we know the force and the distance, we can figure out how much work was done by friction. So
at least they called it work done by friction. So yes, friction is just like moving the cart. It's drag on the thing that was the source of the energy, which is the falling object. So the falling object created the amount of force, and you converted it into either heat work or motion work. But that's it. It's all the same amount of energy. All the energy is accounted for, not a problem.
Let's give this a try. I'm going to set up a slightly different graph, so let me change this around a little bit. I want a velocity versus time graph. And for a velocity versus time graph, the slope of the velocity...
So, unfortunately, he didn't do this for the actual experiment, right? Because that's the one we want. The time. We don't want to multiply the velocity times the time. That's not again, you're multiplying time times time again. So that's not going to help you any. It's just, force times time. That's the one you want.
Versus time graph should give me acceleration. So let's see how this works. So I'm going to give this a little push and start collecting some data. Okay, so let's scale that graph. And notice it is slowing down a little bit, so there is a little bit of friction acting on this graph. And let's get the slope of that graph. So the slope of this graph...
So this is, like I say, it almost looked like a flat line, but this is the detail of it. All right, so, but we don't have any, this is 0.35, 0.3, 0.25, 0.20, over the length that it traveled, how much did it lose to friction. And so this is the chart that will give you the number where the, half the velocity in 1/4 of the distance.
The acceleration of the object is 0.046. So let's write that down over here. We have the force of friction.
So he's saying the deceleration? So he didn't pay any attention to, he just starts with the initial speed, and then he's just doing the deceleration. Okay. And again, that's completely friction decided. So that will be consistent with kinetic energy theory in the sense that, yes, friction's not even per foot. Now, somewhere in here he did make that argument where he cut this into slices and said, oh, look, it's even amount of force per foot. No, it isn't. It's per time.
Equals the mass of the object times its acceleration. We said the mass before was 0.897, I think was the approximate value. And our acceleration is 0.046. So if I multiply those together, 0.897 times 0.046, I get the force of friction is 0.041 newtons. So the force of friction is 0.041 newtons. Okay. Well, we also...
So, but it isn't, because it's not the same per velocity. So the faster you're going, the friction is less. The slower you're going, the friction is higher.
Also said that the distance this thing traveled was around 0.6 meters. Again, it varied from trial to trial a tiny bit. It might have been a little bit less, a little bit more, but the distance that it traveled was around 0.6 meters. Okay. So if we use this work formula, saying, well, the distance that it traveled and the direction of that frictional force, those should be opposite each other, we can say the work done by friction should be the negative of 0.041 newtons times 0.6 meters. And if we plug that in, 0.041 times 0.6, look at that. We got the work done by friction should be negative 0.0246.
So again, this is all just circular math. These formulas are not rational things to multiply by each other. And what but it is a fact, okay, that the friction, this is the actual heat friction, okay? So these little losses of, 2%, it only looks like 1% to me, but anyway, those losses are all there is, okay? And the rest of the energy went into the cart.
Joules. That is really, really close to this disconnect that we had between the work done by the string pulling on this and the change in kinetic energy of the cart. That puts this into a really, really close agreement. In all of these trials, we seem to be finding that the net work really is equal to this change in kinetic energy. Again, work being defined as...
So again, it's just silly, this change in kinetic energy, which isn't indicating what it should be indicating, which is twice the velocity, 4 times the energy. And that's not the numbers you have.
The area under a force versus position graph, or this F times the change in position times the cosine of that angle. This seems to be matching up very, very well for us. So I would say this is very strong evidence in support of this work kinetic energy theorem.
So I'd say it's zero evidence, okay? It's complete circular assumptions. So your assumptions are confirming your assumptions or confirming your assumptions, and none of it has anything to do with any measured amount of energy. So you didn't light light bulbs, you didn't do anything with this energy to show us there's 4 times as much energy in the thing going twice as fast. So I make something go twice as fast. Your theory says it has 4 times the energy. That is, it should be able to generate 4 times the wattage. You have zero evidence in 350 years indicating that is true, just as you have zero evidence that it takes 4 times the fuel to go twice as fast. You have no experimental evidence demonstrating that to be a fact. And what we do have a ton of experimental evidence demonstrating is that rockets, the faster they go, the less fuel they have to use per foot. That's an absolute fact. The faster I get into space, the less fuel I'll use. Doesn't matter what the distance is. Whatever the distance is, the faster I go to that distance, the less fuel I'm using per mile. Now, obviously, if I way overshoot, okay, I'm going to use a preposterous amount of energy and I'm not going to gain anything. So we're talking about using enough launching velocity to use all of your fuel. But that's the rule. The fact is your gas mileage goes way up if you can increase the time you spend fighting the force.
But let's keep testing this under more and different conditions.
So this didn't test any condition, right? So this wasn't showing us how the speeding bullet has 2,000 joules and the gun recoil only has 2. So it didn't show us this 1,000 to 1 difference. It didn't show anything like that. It didn't show the 5-ton train going 10 miles an hour absolutely kicking the butt of the 10-ton train going 5 miles an hour. Didn't show anything like that.
So before we go into another experiment, I just wanted to point out a couple of things. I went through the numbers, and our worst trial on this one for comparing the work done, the total net work done compared to the change in kinetic energy was trial 2. And if we consider both the work done by the string that was pulling on the system and this negative work done by friction, when we combine those two together, the net work done during this trial was around 0.479 joules, and our change in kinetic energy was 0.485 joules. If you take the difference between those two, and then say, well, what fraction, what percentage of this original energy was lost, you get, if I quickly run these numbers, I got less than 1.2% error. 1.2% error.
Yeah, well, that's what I could see right here. I mean, this number is, this is 720. This is 21. Okay, this is 419, and this is 485. This one is the key one, right? Because that's the first unit. It's 2.24. This is 0.24. So it's basically telling you per experiment, this is how much friction you're going to lose. You lose the same amount. It doesn't matter much that you change the weight. And what really matters is that you're actually rolling the objects. You have angular momentum that you're creating, and the angular momentum is essentially the same. It's not enough of a difference to create a difference in the friction.
I did the same calculation for the other two trials. Both of those were less than 0.5% off between the matching of the net work done by the different forces that were acting on this object as it moved down the track and our change in kinetic energy. I'm really happy with these results. I was hoping for less than 3 or 4%. This is much better.
So this is like talking as if there's some grand success here, and all he's saying is that yes, the experiment does isolate what we're trying to isolate. We're trying to take the energy from the dropping mass and put it into the cart, and we did that successfully. That's all. Okay, so that's not the success. Okay, that doesn't prove MVV. Okay, it doesn't prove that MV fails to get a good answer, that MV doesn't get a perfectly correct answer, a perfectly consistent answer. If I just measure the mass and the velocity of the objects, I can perfectly equate the mass falling in gravity to the mass, the motion of the cart. The energy of the mass falling will go into the cart moving.
So this really seems to support this work kinetic energy theorem. Another one or two things that I quickly wanted to mention is our work equation. We said if the force is constant, the work done is just the force times the displacement, and that's the same as the area under the graph. Well, for this graph, when we had a constant force...
So now he's saying the displacement, right? So they use position, distance, and displacement. They all use these different words, okay? So why say the displacement? Why play this game? And clearly the friction is not consistent. The faster the cart moves, the less friction there is. Fact. Okay, the faster I can travel across the surface of a scale, the less I will weigh. Okay, so if I go a certain slow speed, yes, I'm going to weigh the same, it doesn't matter. But if I get up to a fast enough speed to counteract the 9.8 meters, that is a little faster than 9.8 meters per second, I'll start weighing less and less and less and less. The faster I go across the scale, the less friction, the less contact, the less I can lose to the spring. It is losing energy pushing the spring. I'll lose less energy the faster I cross that plane. Obviously, speed and friction are not linear. They're not linear in the sense that they're not the same. Distance doesn't determine friction. Time determines friction.
The area under this graph just makes a rectangle. The area of a rectangle would be the height of that rectangle, so this would be the force in that case.
I mean, that's my assertion. Friction is a time dependent. Gravitational friction is entirely time dependent. It matters on how much time you're enduring the friction, the contact, not how far you travel as you do the contact. Okay, the real proportionality is between friction, the force, and time. That's the assertion. Distance is not an indicator.
And the width of the rectangle would be our change in position, our displacement during that section. So this is just one example of how, if the force is constant, we can actually match it up with this area under a force versus position graph. One last point to mention is when we have this constant force, every time the...
So this is the part, right? So now he's trying to say that every unit of time is the same amount, every unit of distance is the same amount of force, when obviously it's not, in the sense that it's the units of time, not the units of distance. So again, if this was a timed chart, it would look entirely different. This chart would be very narrow here and very high here. So he's, but whatever.
Cart moves a small amount, we're adding the same amount of energy to our system. So every time I move by a certain small distance change, if this force is constant,
Right, you're adding the same amount of force, that is pressure, all right, and the pressure is completely time dependent, though. How far you traveled as that force was being applied doesn't matter. How long the force was applied. So again, this is very deceptive because this looks like he's measuring how long it traveled and he's measuring how far it traveled. So this isn't true.
we're changing the energy by the same amount. That force is adding the same amount of energy each time, which means our kinetic energy is going to go up by the same factor each time. We get this nice linear graph for kinetic energy versus position. Again, this is only the case if we have a constant force being applied. So as the position changes, the force is...
This is not the same chart. So this isn't the force chart. This isn't when he pushed the cart. All right. But it doesn't really matter. The point is that in the first, when you decelerate something, allow something to decelerate through friction, the fact is that in the first 3/4 of the distance, it's the same contact with the surface. That is, the same weight goes into the ground in that much distance as weight goes into the ground in the last quarter. The last quarter will weigh the same amount as the first 3/4 of distance. The amount of friction absorbed, the amount of energy absorbed by friction will be the same for the 3/4 distance as it will be for the last quarter. That's Galileo. That's 500-year-old physics, and it's absolutely correct. And all of this challenge you're putting towards it, you're not going to put it towards it with any physical evidence. It's just theoretical mumbo-jumbo. This is mathematical chicanery.
This, again, is a
9.8 meters per second, and you're measuring feet. I mean, it's that obvious a chicanery, right? I mean, this isn't like hidden shenanigans. The shenanigans is right in your face. A 9.8 meter per second force is being turned into a 9.8 meter per foot force.
A pattern that we can identify that since this kinetic energy graph, this kinetic energy versus position graph is a straight line, when we have this constant force, that supports this idea of the work kinetic energy theorem.
No, it doesn't. So again, that's just more babble. Again, if you compared momentum's analysis versus their kinetic energy analysis, you'll find that momentum is completely conserved and completely understandable. The momentum of the falling object versus the momentum that went into the cart, they will equal each other, no problem.
So we've seen this case of the work kinetic energy theorem being applied to the cart when I apply a constant force to it, but what if I have a force that varies with position?
So as I challenged you, what if I take all of the energy from a heavy object going slowly and I put all of its energy into a light object going fast? What happens then? Like a lever, for example, or a compressed spring. I store the energy in some way, and now I change the mass. Do I conserve the momentum? If you believe I conserve the momentum, I will, in fact, not conserve the kinetic energy. That's the truth of the theory. The two theories are not in any way compatible. They only get consistent answers. They only conserve energy when you use same mass transfers. As soon as you transfer completely all of the energy between two objects that have different masses, you will end up creating free energy or mindlessly destroying energy. Like in the example I gave of the simple experiment where you have a 5-ton train, you add 5 tons to its weight, and you reduce its velocity in half. Exactly consistent with momentum. You have the same exact momentum before, the same momentum after. The fact is you don't have the same kinetic energy. Somehow you magically lost half the kinetic energy, and yet you didn't use any momentum to do it. So you made sparks, or you dented something, or you heated something, or you banged something, and you made horrible sounds, yet you did all of this stuff and you didn't use any momentum to do it, which is an irrational theory, plainly. You must use energy to make something energetic. You can't bend the metal for free.
So the setup that I have right here is I've attached a spring to this force sensor. So instead of having a string going around the pulley with a hanging mass, I've got a spring attached to it, and the more I stretch the spring, the more force I'm going to get. So as the cart moves, the spring is stretched by...
So he doesn't want to say, oh, well, according to Hooke's law, twice the compression is twice the force. So he doesn't want to say that. Twice the weight, twice the pressure.
Different amounts, and we're going to generate a different force. So let's first make sure that the force sensor is zeroed, so nothing's attached to it. Our force is around 0. That's good. And let's stretch this and do the exact same kind of experiment, but this one will be with a varying force. So let's take some data. Here we go. Okay. So for this one, let's again select our data. Let's go with something that looks like that. We've got the area under our force versus position graph is, we've got 1.238 joules.
So force versus position graph. So the force on the sensor goes down because, yes, the sensor is basically declining. So we don't even know how fast the force sensor can do that. But the truth is the pressure the spring is applying goes down as the spring starts contracting. Okay, that makes perfectly good sense.
And let's look at the same region. So for this graph, we're going to highlight the same region as close as we can possibly get to the same.
So it's kind of a funny curved line, which that doesn't seem exactly correct, right? Why is it a curving line? It should be a pretty linear increase in the velocity. So obviously this is a spring irregularity, this curve in the line.
Same region. And let's look at the statistics. Our change in kinetic energy looks like that was 1.172 joules. Again, we still get this effect that the work done by the spring force in this case is a little bit larger than the change in kinetic energy. So let's do 1.238 minus 1.172. What was the difference? I got 0.066 for the difference in those, and we know that there's still probably going to be a similar amount of work done. So let's work done by friction. So let's subtract off that part that we can reliably say is affected by friction, and the amount
somewhere in here, I guess he calculated what he says the spring produces. I don't know. We don't get to see that.
Accounted for is 0.0414 joules. So if we compare that to what we started with, again, it's a little bit further off than some of our other tests have been, but let's see what the percent difference is. I got 3.3% off. So even in this case where we have a force that varies with position, we still get this work kinetic energy theorem being satisfied to a fairly accurate degree.
It's the same work equation. Again, he's just measuring the force over a distance rather than the force over the time. So again, it doesn't mean anything. But okay, whatever.
The area under that force versus position graph is pretty much the same as the change in kinetic energy.
He didn't do two experiments here. So he didn't compare twice the compression of the spring with half the compression of the spring. We need something to compare it to. There's no comparison here. He's just telling us how many joules he says the spring has, and this is how many went into it. So there's absolutely no actual test where we're comparing two different experiments. It's not very useful at all.
Again, there's always going to be a certain amount of measurement uncertainty in any calculation that you're ever doing.
So do it with half the spring compression and show us that it's, half the compression is somehow not half the force. That it's 1/4 of the force, or whatever the rule would be.
And one other thing that I want to kind of point out here is when we have this force that is varying with position, in the case of a spring, we get this triangular force versus position graph. When we look at this equation for the potential energy stored in a spring, the potential energy stored by some conservative force is directly related to the work done by that force as you go from one location to another. There's a couple of technical details in there, but in this...
I think that's a concession to Hooke's law, so saying that there's a linear relationship.
Case, if I have the area of this triangle, well, the area of a triangle is going to be 1/2 base times height. So let's compare how 1/2 base times height for that triangle will compare with this potential energy formula. Well, we have the 1/2 already.
So the potential energy formula is 1/2 kx squared. So he just said he's basically going to sit there and do exactly that. He's going to do the 1/2, okay, and square of the square. So there's no surprise here.
Base of this triangle would, if I went all the way to when that force goes to 0 and the spring is no longer stretched, the base of that triangle would be the stretch distance x, and the height of this would be the maximum force that you get when that spring is stretched by a distance x. The force of a spring, when you stretch it by a distance x, the force of a spring is equal to k times x. So if I have this area, let me scroll down to give me a bit more room.
So again, he's talking about the area, but he's talking about k times x is the force. So the force isn't squared, but somehow the kinetic energy is squared. So right there, you're saying what? How is that going to work? How could you get the same force and the same kinetic energy if in one case you're squaring the number, in the other case you don't?
The area is 1/2 base times height. The base of that triangle is the stretch distance x. The height is the force of the spring once it's at that stretch distance x, so that's k times x. So what we get is 1/2 kx squared. It's directly related to the equation that we have for the potential energy in a spring. And in some of the other examples that we're going to look at, we'll actually...
So again, the kx is just telling you that, frankly, twice the compression of the spring, twice the force. Okay. Newton tells you twice the force, twice the velocity.
We see this spring potential energy formula come into play, and we will give that its own individual test. But as far...
All right, so these are the kind of tests. He's just going to do circular logic tests, so circular reasoning. I will come in with a fake formula, and I will confirm my fake formula with a fake formula. Yeah. I can do that too.
As far as
but I wouldn't.
The work kinetic energy theorem goes, we've tested this again with constant forces multiple times and got very, very good agreement.
So he did the same experiment multiple times, and it didn't mean anything, frankly, because he didn't compare half-mass cart versus full-mass cart, for example.
Especially when we took into the account the work being done by friction. Again, our worst case there was off by only 1.2%. And now we've looked at a case where the force is changing with position. And still, when we apply this work kinetic energy theorem, we're still within just a few percent of having those two terms match. So this seems to be strong evidence in support of this work kinetic energy theorem.
And it has absolutely no connection to the counter argument, which is, well, what does momentum say? And momentum gets perfectly rational answers. Momentum will tell you how much momentum the falling object had because it's collecting the force at 9.8 meters per second. You just calculate how long it took, and you'll know how much force in total went into the string, and then you just figure out that, well, it's a small amount of losses to friction, so all of that force went into moving the cart. And momentum will get perfectly correct answers. Perfectly consistent answers.
So I think I'm actually going to break this video up into multiple parts. I do have a few more experiments that we're going to be going through, and I think if I put them all into one video, it's going to be a...
So let's just say cliche theater experiments, okay, to support the religion. So this is just the Catholic theater that we're going to, and we're going to hear about all these little characters, and they're going to do a little play and do some pantomiming. But they're not going to show us it taking 4 times the fuel to go twice as fast. They're never going to show us that. The consequence of their theory will not be revealed. They're not going to show us a lever not conserving momentum, because it has to not conserve momentum to conserve kinetic energy. That's a fact. So they're not going to show us that. They're not going to show us anything real. They're just going to play these little silly number games and manipulate this bullshit and fool you. And that's all they're doing. They're just molesting the minds of the youth, okay, with a religious dogma. They're just programming people, conditioning people. They're just playing games with their understanding by describing it by saying position or displacement or distance when it's 9.8 meters per second.
really, really long video. So I think I'm going to break this one up into parts, and in the follow-up to this video, we'll look more specifically at some of these ideas of different kinds of potential energy and how conservation of energy is applied to
So
different...
more bullshit about potential and kinetic, when kinetic shouldn't be called kinetic. When you're comparing it to potential energy, you ought to just say active energy versus stored energy. There is no such thing as potential energy. When you gain hydroelectric energy, you're not taking potential energy. Right? You're taking energy from actual falling water.
cases.
Water with a velocity. Weight with a velocity. Mass with a velocity. That's what you're taking. Alright, so that was just horrible. Alright, so I guess I'll do a few comments and then I will... there's one other point to make. I mean, I can make another illustration that in my opinion just, makes it impossible to defend this mush. And such. But what I'm going to do first is pause you for a moment. Yeah. And which I can't do, so I have to get some nicotine. So you'll just have to wait until I'm back. Alright, that should do me. Oh. Hi, honey. I'm home. So where am I? Yeah, that's what I needed nicotine for. This is all so tedious. Jeez. It's like being in prison. Just constant noise, constant bullshit, constant aggravation, constant bludgeoning of the senses. Alright, Richard, some kind of new name. Pipistripisi. Look here, look, listen. Whatever. Let's say you've got a car and I'm pushing it on a flat road, no hill, no slope, just whatever. Me and the car, yeah? Now, this thing isn't getting any faster, but I'm sure as hell doing work. Yeah? Where's the work I'm doing going? Into the ground. Break it down for me, physics style, whatever all that mush is. All there is the fact that everything that's sticky, okay, is sticky because of gravity. Okay, anything that you can't roll or push. If you were in space, you could get the idea that, yeah, it'd be really easy to push the car. Really, much easier. Because you wouldn't have the big, huge, monstrous, horrible friction in your way. But the fact is, you can only make the car go as fast as you can go. Now this thing, okay, so this is Bruce answering his question. The work you are doing is being converted into heat. Okay, there's a lot of friction and other forces. There's not too many other forces besides there simply being you're losing a whole lot of energy because the ground is in contact with the car and it's being pushed into the ground. Okay, harder or as hard or substantially hard, which means you have to keep pushing it out of the friction. Alright. Forces tending to slow the car down. So air resistance really isn't doing it. So there's not a whole other bunch of forces. There's really just the contact with the ground. And the fact that it's being pushed into that contact. The contact is a substantial force. And the faster you can get the car going, though, the easier it'll get to push. Alright. Let's see. Especially if the transmission is connected to the wheels. Well, I mean, do you really need to do that? I mean, what moron could possibly push a car where the car's in drive? That would be impossible. To the engine, you'll be turning the engine over as you push it. Yeah, there's really zero chance, right? I mean, I don't think you could actually push a car that's in gear, a human being. I mean, unless you're pushing it over a cliff, or, I don't know. You notice it's a lot easier to push the car when the neutral, in neutral. I mean, Bruce, I'm sorry, but wow. I mean, Jesus. There's some things you could say that only 1 in 100 people know what you're talking about. But what the fuck? Do you really think somebody needs to be told about having the drivetrain in gear and how turning the engine over would be like an insane amount of energy for you to produce on your own? All right. Appreciate the breakdown, pimp. Okay, Richard, you're just too cool for, you're just too, what's that song? I'm too something for my something. You're just too something, right? You're just too cool. So you really can't be in this room because, people as cool as you can't be in here. You little pimpy talk. Hey ho, what's up? What's up? I mean, off to slag a Pepsi. You won't catch me later, okay? At least not that I'll know of. Because fuck you. I mean, god damn it. Creatures. These are just creatures. These are not human beings with a brain. I mean, it's just, what is it wrong with people? Oh, it's just, god damn. It's like, I mean, it's like Valley Girls doing physics. I mean, fuck. Sorry. I just can't take it here anymore. I just can't. I need a bus ticket off this planet. The prediction when doubling the mass, twice the mass over the same distance means double the energy. Okay, I don't even know. The prediction when doubling the mass, twice the mass over the same distance means double the energy. Well, if it's twice the velocity, will you concede that that's not consistent with reality? Shit. Yes, he's too sexy, for the chat. He's too sexy for the chat. Way too sexy. Oh, God, I just hate this planet. He probably has troll accounts like Big Dick, Mr. Big Dick. It's just... God damn. I just hate it here. I hate it here. I hate this fucking shithole. Oh, God damn it. Fucking stupid everywhere. The idiocracy has spread. It's all fucking Einstein's fault. Fucking stupid boogerhead. Anyway. Well, it's obviously Leibniz's fault, but whatever. Everybody turned into a fucking sissy. Okay, it wasn't reaching twice the velocity. It would have been reaching about 1.4 the velocity. So where did you demonstrate any of that? The number said twice as far as I could see. But anyway, fine. That's your theory. Okay. You're not demonstrating it with any evidence, so I'm just saying, keep saying levers only let things move 1.4. If I keep saying it, you don't have to conserve the momentum. I'm saying, yeah, you do, so I think you're screwed. But whatever. Alright, let's move on to a bit of reasoning that should just end this stupid moronic crap with these people and this crappy physics they're propagandizing for which they have no physical evidence. So I have a human being, okay, and I give him a velocity. I say run, and he's running into a spring. Okay, so the human being weighs 100 pounds, okay, and he's going to run with a velocity of, let's say, 5 miles an hour. Just make up any numbers, it doesn't matter. So 5 velocity, 100 mass. Okay, it compresses the spring. We'll just say it compresses the spring this much. Okay. Now I take another guy and I do exactly the same thing. Okay. Yeah. At a different time, it's exactly the same thing, right? And it compresses the same amount, right? Okay, so that we know. But what if I have both of them, okay, go at the same time? What happens here? What happens? 2 guys, 2 weights, same velocity, 5 miles an hour. So it's now 200 mass, okay, at the same 5v. What happens to the spring? Well, I'm arguing, obviously the spring compresses twice as much. Exactly twice. 2x the compression. Okay? No problem. Makes perfectly good sense. Momentum is conserved. Everything makes sense. The spring constant, Euler's law, blah, blah, blah. It all fits. Hooke's law. No problem. So, their theory is that, if I take one mass, okay, one guy, and I go 10 miles an hour, all right, that I'll compress the spring 4 times as much. Yeah, it's okay, right? This isn't exactly the way I wanted to draw this, but let's just do it. Okay, so this is 100 times 10. Okay, and that won't equal 200 times 5. That this one thing will be twice as much compression as this thing. So this one thing will somehow double this compression. So even though it's the same momentum, it will create another 2x, all right, the force. So one guy going 10 v, right, has twice the energy of 2 guys going 5, and one guy going 5 is 1/4 of the energy of one guy going 10. So they're basically saying this guy is only 1/4, okay, of the energy of this guy going 10. Now, to me, this doesn't rationally make any sense at all, that this is nonsense. This is going to be the same distance, okay? This will equal this. This is not equal to 2 of this, okay? If 2 of this hits me at 5, it's going to weigh the same as half the mass hitting me at 10. Same difference. There's no difference in the weight. The pressure it can apply is exactly the same. It's the same amount of weight. 100 times 10 is the same weight as 200 times 5. It's the same weight. They can't weigh different. So their argument is, okay, that the spring is storing kinetic energy. So this is where it gets even weirder. So they're saying that somehow this doesn't compress the spring twice as much. So even though it's twice the energy in, I have 4 times the energy to give out. Somehow the compression of the spring is 4 times what I put in. Because if I want to, I can launch the 1, okay, at 10. All right. With the two 100s going in at 5, I can launch the 100 going 10. Right? No. 200s 5, yes, will equal 100 at 10. That's what momentum says. Well, I thought I had this all arranged in my brain, and I obviously fatigued myself in the previous video. So anyway, they're saying that this will not compress the spring twice as much, or they're saying that yes, it will, because it's 4 times the energy. How could this be 4 times the energy? It's only 2 of this. How can 2 of this, 2 times this, okay, equal 4 times the energy? It's only 2 of these. That's all I used, is 1 work, 2 works. I apply it at the same time, I end up with a spring compression that's 1/2, which you say is really 4 times the energy. So I can get this to 20 miles an hour. Yeah, so I can put 2 two 100s in, and I can get one 100 going 4 times the speed out. That's why I'm saying their disconnect is. It doesn't add up. You can't make it make sense. There's always somewhere it's going to break down and it won't make any sense. You can't say this has a unit of energy and then say I only have to use 2 units in to compress the spring and I can get 4 units out. I can't put 2 units in and get 4 units out. So either the spring compresses twice as much, which it has to, it's twice the weight, there's just no way of turning that around. It's just like if we were just doing it in gravity. All I did was put a player in and a player in. I got put 2 units of energy in. How can I possibly get 4 units of energy out? It's irrational. Didn't do it as well as I had hoped, but whatever. The point is made, as frankly, you can duplicate all of these gravitational experiments by just giving something velocity this way. The scale works just as well this way as it works this way. It measures weight, pressure. It does it just as well this way as it does this way. Oh, God. Anyway, let's see. He wasn't reaching twice the velocity. It would have been reaching 1 point. Okay, so there's just we have no evidence of that. So that's just you say so. Because the distance was constant. So again, the distance is irrelevant. It's 9.8 meters per second. So everything I said in this video, he just ignored everything I just said. He's just pretending it's about distance. I'm pointing out how distance has nothing to do with it, because the faster you go, the less gravity you collect, or the less force you collect, and therefore the less force you can put into the cart per unit of time. Just a fact. But okay, keep saying it over and over and over again, and yes, that will be an impasse, and we'll just say forget it, because you're just not countering my argument at all. Okay. These guys are constantly running, producing a constant force into the spring. I don't know what these guys are. No, they're running a velocity. They have a momentum. Just like a falling object has a momentum when it hits the spring. It has a momentum. Oh, there's just no hope. Let's see. Are they constantly running? They're going a velocity 5. Shit. Producing a constant force on the spring. They don't produce a constant force on the spring. They produce an impulse force on the spring. They hit the spring with a force. All of the force goes into the spring because the direction is right into the spring. It can't go anywhere else. It has to go into the spring. So all of the momentum of the object is collected by the spring, and you get a maximum compression of the spring. The number has a maximum, and all you're saying is as you hit it, there's a maximum amount of force I hit this thing with. There was a maximum amount of energy that went into it, and that was measured somewhere. We couldn't see it because I did it so fast. But the fact is that, slow motion camera can see it. Even some frame rate cameras can see that. So you can see what the maximum number is. That maximum number is a measure of the energy you put in. The spring does not go the other way until all your energy is used up. You're using up all your energy. You're putting it into the spring. For a tiny millisecond, the spring has the energy. If you just had a spring that locked, that is, the further it goes, it just locks at the furthest distance, then you have stored the energy of the object. I mean, I have to go through all this. Anyway, are they shot into the spring from a cannon? It wouldn't matter, theoretically, right? Because we're saying air resistance isn't a big deal here. We're going 5 miles an hour. Yes, they're going 5 miles an hour. They have a velocity, 5. And just have whatever energy the cannon gave them. So, whatever. You can't get any simpler, right? 100 pounds moving 5 miles an hour. That's the energy. It's a bowling ball rolling down the frickin' Nile at a velocity. It hits the pins going a certain velocity. That's its energy before impact. Oh, fuck. Anyway. If you compress a spring with 200 mass going 5... and use that compression to push a 100 man, you would get 5 times 1.4 out. So you say it. I'm saying you have no experimental evidence. None. And what you're saying basically breaks conservation of momentum. So you're saying there is no conservation of momentum because it won't be the same momentum then. So where did the momentum go? So we're right back to the lever. I mean, there's no point with you, right? I mean, I have the lever. I put the 2 mass on this side. I put the 1 mass 2 units of distance. It oscillates perfectly. How do you think it's oscillating perfectly? This is going twice as fast. Half the mass, twice the speed. Not 1.4 the speed. It has to go twice the speed. That's 4 times, okay? So I'm just saying, by Newton's laws, that's what you're going to get. I'm just saying if you say it has 4 times the energy, you have to say, okay, well, what's 4 times the energy in terms of if the mass is staying the same, how can I make 4 times the energy? I have to increase the mass, the velocity. If you're going to conserve the momentum, you have to go 20 miles an hour, okay? 20 V. So again, just say it again. You don't believe in conservation of momentum. Shit. The excess momentum went into whatever is holding the other end of the spring. So somehow the spring could tell the difference between exactly the same weights. Yeah, says you. So this is all just says you. You have no physical evidence that any of that happened. You have no experiment showing it happens. It's just made up. Just like when you make up half the energy loss when I add 5 tons to the 5-ton train. I make the 5-ton train, 10-ton train. You're saying half the energy of the train was lost to sounds and stuff. Yeah. You'll never show it. You'll never show the heat. You'll never show any of it. Adding up to half the momentum of the train. Ever. You won't even come close. All you'll account for is the 0.0024 losses to friction, an increase in the friction. It's not my job to make claims with evidence. I'm not 300 years. I am not $1 billion science, okay? They have an obligation. If they say light is bent twice as much by gravity, don't you think that's an extraordinary claim? They're saying, okay, against Descartes, Newton, and Galileo, all people who got right answers, they're saying those 3 people were morons and idiots because they didn't see this obvious, super cool energy, this VV stuff. Okay, so yeah, they saw mass, velocity, they saw it worked, they used it, it worked. Okay, they make a challenge and say, no, it's 1/2 MVV. Okay, multiply the velocity times itself for no frickin' rational reason. And yet they produce no evidence to support the theory. You're saying that's the way science works? Energy is not momentum. Yeah, we've heard that before. Says you. Okay? Newton certainly thought it was. Descartes thought it was. And Galileo thought it was. And you haven't demonstrated how they were wrong with an experiment that shows them to be wrong. Show where momentum gets a wrong answer. Momentum gets the right answer with the gun and the bullet. Your theory says somehow, magically, again, you just ignore every argument made. I stick a gun inside of a gun with the same amount of dynamite. I fire the dynamite, the 2 guns fly off, I have 4 joules of energy converted. I've taken the energy from the explosion, I made 4 joules of energy. I take a hollow tube and I put 2 bullets in, but with 1 charge, the same amount of explosive. I fire the explosive. I have 4,000 joules of energy. Same dynamite. 4,000 joules in one case, 4 joules in the other case. Where have you countered that argument? I'm saying I don't have an obligation to do all the experiments in physics. I don't have an obligation to do the Eddington experiment from my basement. Okay? I don't have the technology. I don't have a laboratory. I don't have trillions and billions of dollars. I don't have, just think how many technicians there are, on this planet right now with very sophisticated electron microscope access, all kinds of stuff. I don't have any of that stuff. They have it. They haven't proven their theory, okay? It's not my obligation to show up and do all these elemental experiments. Don't you think somebody should have done the fucking 4 times the fuel to go twice as fast experiment in 300 stinking years? You think it's okay that they never did the experiment? I think it's outrageous evasion of a fact. The fact is it doesn't work. That's why it doesn't exist as evidence, because every single time they ever come close to trying it, it doesn't work. Just like the Mythbusters crashing the cars never crash 4 times as much. Newton said it quite clearly. You want twice the velocity, twice the force. He said those exact words. You want twice the motion of an object, inject twice the force. Clearly, the association between him, his diagram of his mathematical diagram of gravity, and more specifically his mathematical formula. Force equals, change in your momentum over time. If the time is net, that is the total time of the experiment, then obviously you're detecting the net force, the total force, which means you can just cross the T's out and you just have momentum equals force. And that's exactly what he said in his second law. He said it right in his second law. You want twice the velocity, just add twice the force. You want 3 times the velocity, add 3 times the force. He called velocity motion. You want twice the motion, twice the force. Look, Nikki, you're just going to get blocked, okay? Again, I have no obligation to buy something they have hundreds of thousands of. And what air track experiment are you going to do? I've already shown Professor Lewin had a $15,000 air track and he cheated. Yeah. And again, I did the experiment using a ballistic pendulum. And I didn't get any free momentum. Then what is energy to you? I don't know. Whatever this conversation is, I don't know. Let's see. Energy is not momentum. We both do. Neither of us are doing experiments. Okay, I don't know what that means. Again, I'm not the one, again, who challenging Newton, Galileo, and Descartes' good reasoning and good theory. And frankly, good experiment. Descartes did a ton of experiments, banging things into things. You have the money to buy an air track, whatever that means. Then what is energy to you? Obviously, I don't have a lot of money, but whatever. Then what is energy to you? I don't know what that. Why don't you, instead of soliciting for attention, why don't use it instead of soliciting for attention? I'm soliciting for arguments, you dumb cunt. So just fuck off. This is just such bullshit. I get ragged on because I'm just not nice enough to these pieces of shit. It's just amazing. I'm asking for them to make a counter argument. I'm trying to bribe them into making a counter argument to the actual statement made. Take my gun example, for example, and explain how it works, Nikki. Can you do that? I'll leave the dumb cunt for a while. Let's see if you can come up with some statement that has something to do with physics. Can you make an actual physics argument? Or are you too big a fucking flapping idiot? Momentum equals force times time. There, that's the only sensible statement made on this board today. Twice the time gives twice the momentum. Yes, that's all you need to know. Forces are units, and the units are applied in an amount per another unit, and the unit has to be time. Pressure per square inch. Let's see, that is convertible into the velocity that it'll cause the objects. Because you're hitting a smaller number of objects, you'll obviously be able to give the objects more velocity. So the smaller number of objects you hit, the larger amounts of energy you can potentially give them. The more you hit, the more you're losing your energy, and the less energy you give them. But it's really about, obviously, high-speed objects give all of their energy in a very short amount of time. Very slow things give their energy in a very long period of time. So they give small amounts over a long period of time, where fast things give a high amount in a very short period of time. And obviously substances react to that. So yes, the bullet looks like it has more energy, but looks like isn't is like. Shit. It's just no hope, apparently. Well, we'll see. I mean, we'll see if this guy comes back with something, right? So we'll just see if he just runs away from the real conversation. And, whether he'll deal with any of these real questions about the fact that there's no sign of mv squared in space navigation. If you want to navigate in space, there's no point in you calculating anything's distance. And there's every point in you calculating how much time are you exposed to a force, or how fast is the objects, again, momentum-wise. How much momentum are you throwing from your ship? And that's all that matters, is how much momentum did you sacrifice. Let's see. I hasn't heard you put a gun in a gun argument before. Here's how I think it would go. Well, I've made it like, I don't know, over a dozen times, but fine. Suppose the bullet in one gun and the gun is 1,000 grams. Well, we don't have to do this, all right? We don't have to assign anything. We just, obviously it's 1,000 atoms going 1 mile an hour, and it's one atom going 1,000 miles an hour. And all I'm simply saying is you're saying that 1,000 atoms going 1 mile an hour going that way, and 1,000 going that way, okay, those two groups of 1,000 atoms, it only has 4 joules of energy. And you're saying that the two bullets, when I let the one atom going 1,000, and I make two of those, two bullets going 1,000, that it's 4,000 joules of energy I put into the universe. All right, so I'm not going to accept liars. Okay, so I'm sorry, you're going to get blocked. Just so we're clear, your 2 + 2 theory predicts momentum is energy. Is this correct? It doesn't predict it. It's an overt, absolute, fundamental axiom of physics. Yes. It's a simple answer. But I don't need the 2 + 2 theory. mv squared was wrong before I came up with 2 + 2 + 2 physics. It's just fundamentally a fable. It's living force. It's absolute crap nonsense. It never is accurate. If you actually calculate the joules, it never gets a right answer. If you actually use a 10 mass going 5 miles an hour and a 5 mass going 10 miles an hour, and you actually put a generator on their wheels and you actually extract the wattage, they will produce exactly the same watts of energy. Look, I'm just saying you're just, there's no point, Bruce, okay? You're not going to stay on the subject. Suppose the explosion gives a force of 1 Newton for 1 second. It doesn't matter how long you're saying the explosion is too slow to give the guns the same amount? Obviously, it's not too slow to do that. You're measuring how much energy came out of the explosion by measuring by the stuff flying away. Okay, momentum says it's exactly the same stuff flying away, the same amount of energy. Your theory says there's 4 joules in one case and 4,000 joules in the other case. Which one is the real case? Which one is the real number of how the explosion actually produced? There's no way you can say there was more friction or there was more compression or there was more anything in either of the explosions. We're just calculating there's pieces flying off. There's only 2 pieces in each experiment. 2 pieces are flying off the explosion. In one case, there's 4 joules of energy. In the other case, there's 4,000 joules. Will you actually deal with what I'm saying rather than playing this fucking word game to evade it? Yes, so Bruce again points out the obvious. They don't believe in Newton's third law. There's no conservation of energy when you fire a gun. It's not about using numbers. You're using convoluted numbers. There's no point on putting numbers on it. You're sitting here playing games with how some sort of game. Okay, we already know the numbers. I've already given you the numbers. There are no other numbers to get. You have one explosion, and you're just saying, I'm going to put big objects and see how much they move, and then I'm going to put small objects and see how much they move, and I'm going to say, is it the same amount of energy? And the fact is, by your theory, it's not the same amount of energy. The explosion somehow made more energy when it exploded one way than when it exploded another way. So I could do the same thing with a sun, and I could say if a sun explodes, it goes supernova. And instead of it flying off in little tiny pieces, it flies off in 2 big giant pieces. Your theory is going to say, well, it only had 4 joules of energy. When in the other case, it's going to have 4,000. So again, it's a complete violation of conservation of momentum. It's a complete violation of conservation of fuel. You're saying the fuel is somehow more powerful. Just like if I'm in a rocket, I'm actually going 500 miles an hour. Your theory says the fuel left in my tank has more octane in it now. It actually can make me go more. It can, it actually has more energy in it. So I just don't see what other numbers you need. 1 atom going 1,000 miles an hour, 1,000 atoms going 1 mile an hour. What more do you need? Your theory is one of them is almost nothing in terms of energy, and the other one is gigantic. It's 1,000 times more energy. I'm saying the same force can make both things. Obviously, that's what I'm saying. And those same things will knock down the same door. So if I put up a resistive force, a friction, I apply a friction, okay, to both of those things, they'll break the friction at exactly the same number of the amount of force I put in, because they both have the same momentum. There's no experiment you can do where you'll make the single thing going faster, the 1,000 times lighter thing going 1,000 times faster. You'll never do an experiment where it does 1,000 times more work. Ever, ever, ever. So, I mean, Bruce, it's not a very complicated answer to that question. It just has to do with, again, the fact that glass shatters. It has to do with the fact that all chemical bonds are dependent on velocity. Velocity matters to chemistry. It matters to atoms. Okay, so the faster you get the energy in, the object can't transfer the energy. So you could make the argument that it's like a sonic boom. You've broken the limitations of the medium. That's all you've done. So the faster you can do it, the higher the frequency, the more you can damage something. It's not because it has more energy, it's because you're going to put the energy in a way that can't be dealt with. All right, so it has to start scattering. So that's why the bullet does more work in appearance, is because, frankly, it's applying the energy 1,000 times faster. It's putting the energy into the atoms so fast that the atoms can't keep their direction, they can't keep their energy. They're breaking, essentially. So you're breaking the chemistry, and then you're breaking the tension, the physical tension, when that's built out of the tension between the atoms, right? The bonds between the atoms. So you're breaking the bonds between the atoms because you've achieved a velocity necessary to ionize and break atoms. And without that velocity, you can't. So it's like me arguing that I can shoot infrared light at a metal and I won't produce any electricity. And then I shoot ultraviolet and I produce all the tons of electricity. Well, that threshold has nothing to do with the amount of energy it took to make the infrared light or to make the ultraviolet light. It has absolutely nothing to do with it. We know that the ultraviolet light is just taking advantage of the fact that the higher frequency means the energy can get into the atoms more efficiently. And at the lower frequency, it can't. It's opposing itself. It's yin-yanging. And it's just yinning if it goes at a high enough frequency. So we're just saying that that's a limitation of chemistry. So the simple answer is all you're seeing is chemistry. You're not seeing physics. So the kinetic energy formula, yes, MVV, has nothing to do with reality. That's right. It's not real. It's nonsense. It's rubbish. It's a holy ghost. It's a garbage theory. It's junky theory. It's junky science. It's unproven nonsense. And your theory is reality. So I gather it is correct to say your theory is incompatible with kinetic energy. It's incompatible with MVV. Yes, that is nonsense. Is this a correct outcome? Yes. The kinetic energy theory, 1/2, the original kinetic energy theory, by the way, was just mv squared. It was mv squared for 150 years before they fixed it. Well, for 100 years before they fixed it. It was getting preposterously wrong answers, okay, for 100 years, and they didn't notice. I don't know what this 2 + 2 + 2 thing is. It's called 2 + 2 + 2 physics, okay? You just haven't watched enough videos. debatephysics.com. You'll see a video somewhere in there that says 2 + 2 + 2, no doubt. But if you look it up, there's plenty of my videos that are titled that. Two kinds of force, two kinds of matter, electrons and protons, two kinds of interactions. That's what it stands for. You can be stuck to an object or you can reflect off the object. Those are the two interactions. The two kinds of force are electron force and proton force. The two kinds of matter are protons and electrons. There. That's all you need to know. The physical universe can be summed up by 2 + 2 + 2. It explains charge, explains magnetism, explains motion, explains everything. Explains the formation of atoms, explains charge. No. Might as well pop the simulation up. Oh. the other guy who was supposed to be doing the simulation actually is maybe going to go back into it. So blah 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 blah. But who knows? It must be hard for, I mean, I can imagine it's, difficult for a lot of people to live on this suffocatingly stupid planet. So I can understand their having limitations to their functionality. But there it is, right? So get rid of this piece of shit. Alright. Fucking useless commenters. So all you need are these two simple rules. The force bits move the speed of light. They come in two varieties, red and blue. The blue blobs, the blue and the red blob represent atomic particles. The only two atomic particles that actually exist, electrons and protons. When a red force hits a blue object, it comes out blue. Okay, and that's really a 3 in terms of interactions. Well, we'll just forget about that interaction. The rest of the interactions are just simple. If the object is moving towards the force bit that hits it, then the two bits reflect. If the object isn't moving, then it sticks and it collects it. So if it's moving in the same direction, it can keep sticking and keep sticking and keep sticking, and the object will gain more and more momentum as more and more force hits it in the same direction. The object will start going faster and faster, the electron or the proton. So, and that's the simple rule. And by those simple rules, you create perfect attraction and perfect repulsion. So the charges behave exactly as Maxwell dictates. The lines of force are exactly the same and consistent. It works really well. It duplicates perfectly charged. And once you create charges that stick to each other, you've created dipoles, and dipoles are what creates magnetism. So it's all very simple and it works. And that's the point. It duplicates what you see in the real universe. No gluons, no pooons, no muons, no zooons, none of the bullshit-ons. Completely unnecessary to the function of the universe is all of your made-up fables about fake energy and fake functions. I suppose I could put this down here, and I could put this up here. And nope, wrong one. I want this one. No, wrong one again. How come I keep hitting the wrong one? There's not too many things here. Surprising. This should move up here. Okay, so I move that up here, and then I can move this crappy shit behind that shit, and then that should do it. Yeah, that's good enough. Alright, so let's do a few more minutes of this crap, and I'll just get out of here. It's just very disappointing. Like I said, he said he was going to do a video that somehow responded to my remarks, and he didn't respond to anything I said in my video. Absolutely nothing. The controversy is about what's the definition of energy, momentum or kinetic energy. The two theories are not compatible. It's just a fact. I don't know. I guess if it's a live video, I don't know. The live videos, I don't know, are the best. I mean, obviously I started the live videos by giving a lecture about something, so fine, start there, yes. Whatever. I don't know why you keep saying this crap. Okay, I see. 2 plus 2 physics implies 1/2 mv squared. No, I'm saying 1/2 mv squared was known to be wrong 300 years ago. Okay, all the Newtonians said, you're full of shit, Leibniz. He was buried as a nobody because everybody, except for a few cult members, understood that it's a free energy formula. The whole argument took place. The Newtonians won decisively. Newton was buried a god. Leibniz was buried a bum. Okay, nobody showed up at his funeral. Zero colleagues showed up at his funeral. That's how discredited he was. So don't give me this crap that you need 2 plus 2 physics to understand 1/2 mv squared is wrong. It was understood to be wrong because it didn't get right answers. It couldn't explain a lever, and it still can't explain a lever. They have zero evidence for the theory. Do you understand that? You can't link me to a piece of evidence because there isn't any. Obviously, the Newtonians didn't know what an electron was, you fucknut. I just don't know why you're trying to pigeonhole any of this conversation. Why do you find this necessary? I observed mv squared, completely independent of the fact I already had a counter theory. I just observed that this is a ludicrous statement. 4 times the fuel to go twice as fast. I observed that that was a silly thing for you to be saying. And so that's why I started making these arguments, because I'm just showing it as another example. Just like light bent twice as much by gravity. You don't have any proof that light is bent twice by gravity. You just accept it as some sort of truth, and you don't repeat the experiment that should be repeated. The science is garbage. That's the point of this video. I'm basically saying conventional science is garbage as science. They don't do the scientific method. They aren't careful. They aren't cautious. They leap to conclusions on scant evidence. They make up all kinds of theories based on nonsense, like somehow you can convert mass into gravity, which you can't do. Jesus. Who are you arguing against? I'm arguing against you, you fucking troll. And if you keep it up, that's what you're going to do, is get deleted. Being discredited doesn't mean he was wrong. I'm saying he did, in fact, lose the argument. So I'm saying the argument actually took place then. Are you saying the argument's happening now? Is anybody arguing except me? No. So because nobody's standing up and telling you you're wrong doesn't mean you're right, does it? Because everybody believes it, like believing in Jesus or something, does that mean it's a good theory? No. I'm saying the science sucks. That's what I'm saying. I'm saying your science absolutely sucks. Your lack of demand for evidence is fucking goddamn shitty science. A scientist he says, show me. Show me, fucker. You're going to make a claim? Show me. Show me the picture of your UFO. Show me the picture of your fucking entanglement. Show me a picture of some of this crap that you claim is real. Your Sasquatch theories. That's what a scientist does, and none of you pieces of crap are doing that. You're just completely bigoted, biased morons. Doopy little Catholics telling me, but I can feel Jesus inside of me. Yeah, screw you. I can tell the difference when you put the 2 mass on the lever and when you put the 1 mass 2 distances away, even though it weighs exactly the same. I can tell the difference. That's what you said. Else, what does it say about your theory? Again, this isn't about a theory, it's about an argument. And whether you're making one. This is about a legal standard, okay? You're coming to court and just talking about invisible man. You just keep talking about your theoretical fake invisible man and how he could be the guilty party, and you don't need to blame my client because, damn it, the invisible man could have done it. He could steal his fingerprints. He could steal his DNA. Look, you could steal my DNA really easy. You could just pull it off a tree somewhere around here. Yeah, it's all fake. It's all fake. There's no real... Oh, no, you can't believe... No, that's all you're doing. You're a shyster. You're not making any counter-arguments. Again, I made the bullet analogy. You tried to turn that into some convoluted, complicated thing. It's a simple statement. Does 1,000 atoms moving 1 mile an hour change the universe just as much as 1 atom moving 1,000 miles an hour? Is there the same potential for change, the same potential to spread the energy? Yeah, I'm arguing yes, it's exactly the same potential to spread the energy. Same wattage. All right. Wasn't it demonstrated you can tell the difference? No. Demonstrated by who? Brozo? With a lever that wasn't even balanced? Okay, it didn't have the same mass on one side as the other side? How could that possibly be a balance? Can you make a balance that way, Nikki? You really are dumb, aren't you? terrible. Why are you people so glued to this crap? I point out to you how there's no evidence and you just ignore the statement. In 100 years, they never repeated the Eddington experiment. Just understand, they never successfully repeated it. All right? And it's this bold claim that somehow this magical photon particle, that's a force particle, frankly, that shouldn't be bent by gravity at all, is somehow bent twice as much by gravity. Twice as much. It's a bold claim. And 400 times better resolution from space, 400 times, not 4 times, not 40 times, 400 times more powerful. Your viewing object becomes 400 times more powerful from space. And they never duplicated, never attempted it. We're supposed to believe. Never even attempted it. Takes 5 minutes to do the experiment, and they never even attempted it. It wasn't balanced, so that's a lie, so you're blocked. It's a lie, Nikki. It wasn't a balanced lever. It was a fucking catapult. You're too stupid for the conversation, and you're a liar. I mean, I've made videos debunking all this stuff. I'm not going to redo it and redo it and redo it. I mean, this is just moronic. Yeah, levers, pulleys, gears. Gears was another good example I gave, right? I mean, I have 2 gears, a little gear here in the middle, a big gear out here. What happens when I turn the gear with a force, right? I'm moving one object twice the speed. Exactly the same as the lever. So if I threw things using the turning force, if I put a half mass at twice the velocity, it's going to take exactly the same force as the full mass at half the velocity. Same turning force. The gears can't make energy, right? They can only convert it. And the simple truth is you can convert a 10-ton train going 5 miles an hour into a 5-ton train going 10 miles an hour. You can do the conversion. They have the same energy. I can convert the one atom going 1,000 miles an hour into 1,000 atoms going 1 mile an hour. I can do the conversions. There are devices that will do it. All right, it looks like we're about done. At Nikki. Well, Nikki's no longer here. So. I mean, really, like I said, just saying, I mean, it's obvious. I mean, Brozo's tie a spring to a stick is not really using a lever as a balance, right? A stick with a fulcrum here and no extra stick at the other end, just a fulcrum and a stick, okay, that is hardly a balance in claiming the weights or the, proportional distances. You're obviously having to lift the entire lever with his system. The weight of the lever becomes incredibly significant. Oh, whatever. Oakley doke. Guess we're done. So, till the next time, and such, and so forth, and whatnot. Another fucking... Like I said, just very disappointing. All these arguments are just wasted because people will not address them. So it's just disappointing that this physicist, he just won't imagine that he could possibly be wrong, and so he won't concede that any of these arguments need to be addressed, and so he just debated every fucking one of them. And it's just disappointing. Very disappointing. Only 7 viewers. Wow. Well, fuck that too. No wonder. But anyway, Saturday, I guess. Blah, 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 blah. So, yeah, God.